Atal FDP program. So today we have with us our very well-known professor, Professor KPS Rana sir from NSUT. So Professor KPS Rana sir received MSc degree in physics, electronics major from Meerut University, MTech degree in instrumentation from IIT Delhi, PhD degree in intelligent methods for complex vibration measurement and control from GG SIPU New Delhi. He served ISRO from 1993 to 2000 as a scientist in the sensor division at Laboratory for Electro-Optic Systems, ISRO Satellite Center, Bangalore since August 2000. He has been with NSUT New Delhi in the Department of Instrumentation Control Engineering. He has served NSUT as Assistant Professor from 2000 to 2005, Associate Professor from 2006 to 2011, and currently serving as Professor since 2011. And since November 2021, he has been served working as Senior Professor at NSUT. He has held the position of Dean, Industrial Research and Development from 2018 to 2019. He has been the founder, the Dean of Faculty of Electrical and Mechanical Engineering from 2018 to 2024, and the Dean of Faculty of Information and Communication Technology 2018 to 2023. He has published over 75 SCI research paper in reputed international journals, over 100 papers at international and national conferences. He has supervised 6 PhD theses, 20 master theses, and over 100 UG theses. His current research and teaching interest includes PC-based measurements and control, machine learning, real-time system, digital signal processing, virtual and intelligent instrumentation system, sensor linearizations, modeling and control of solar PV and fuel cell system, and modeling of chaotic systems. He has been elected as Fellow of Institution of Engineers India, IEI, and Fellow of Institution of Electronics and Telecommunication Engineers, CIRO, recognized by DSIR, Government of India, IET. He is the lifetime member of Indian Society for Technical Education, IST, M 56,000. He is a very good number in citations, H index, and ITER index. So, sir, currently, till 20th November 2025, sir has a citation of 4,000, H index of 33, and ITER index of 68. So, welcome to you, sir. Welcome to this JC Bose University for this FDP program. And thanks for accepting our invitation, sir. Over to you, sir.
Thank you, Dr. Saxena, for nice words. So I'll share my screen and
yeah, sure.
You can confirm if it is visible to you.
Okay. Yeah, okay, Kashika, is the recording started?
Yes, sir.
Okay, fine.
So please confirm if it is visible to you.
Yeah, visible now, sir.
Great. And I think I can put my video off so that we are more efficient.
Yeah, sure, sir.
Sure, sir. Yeah. So, good evening, all the participants and the organizers. I'll talk to you for 1.5 hours on the PowerPoint tracking, maximum PowerPoint tracking of solar PV systems. I've been already introduced, so this portion I can skip. And whatever I discuss with you, I present in the 1.5 hour, coming 1.5 hour. So I would like to acknowledge and appreciate the contributions of my colleague. The content which I will be sharing there, in fact, we have a team. So my colleagues are involved with the work, my UG, PG students, and certain contents I picked up from the websites or the internet. So I acknowledge all those, and I would like to acknowledge and appreciate the organizers for giving me a chance to share my viewpoints on the maximum PowerPoint tracking of SPV systems. In particular, I would like to thank Dr. Arya and Dr. Saxena, who has been in touch with me for the past some time. And in fact, Dr. Arya approached us for the lecture, and I suggested we can have one topic on maximum power point tracking. So broadly, I work in measurement. Our department is measurement, is the instrumentation and control. So am I audible to you? Please confirm once again.
Yeah, yes,
Yes,
sir.
sir.
It's audible, sir.
You are
And
audible.
I would appreciate if some participants should make it interactive so that we have a fruitful session.
Yeah, sure, sir.
Yeah,
Sure.
please feel free. Otherwise, it will become one way. Right. So let us see how we proceed. I'll try to motivate also. I'll try to have some queries, some so that you are motivated in between the lecture. So broadly, we work in measurement. Measurement that includes sensors and sensing systems, DSP, robotic manipulators, intelligent instrumentation. In particular, we have done good work on FPGA. And after that, we shifted to renewable energy. That includes modeling and control of solar power systems and fuel cell to some extent. And we also have the work on the MPPT under the uniform shading and partial shading both. Then partly we did try the load frequency control of power systems. And followed by recently we shifted to machine learning, which includes applications of machine learning in biomedical signal processing, classification, recommendation, maximum power point tracking, emotion recognition, and robotics. And we did some work on optimization techniques also. In fact, 2-3 algos we have developed. And all of these work were well received in the SCI publications of international repute. So this 1.5 hours I plan to dedicate on requirement, need, challenges of solar PV systems, modeling of a PV system, and I'm very sure some participant might be interested in research. So I'll try to, in fact, I'll put the content from my own research. So whatever we discuss, you'll find in terms of papers, publications, apart from some motivations. So that would be, I hope so, useful to you, and you can take up. It might lead to some other extension work. So kindly attend carefully. So modeling of PV system, we have tried. We have, in fact, a few papers on PV system modeling. Then maximum power point tracking of PV systems. Then deep learning, load frequency control. So I'd like to leave it to this talk to majorly the first 4 components. And if we get time, we might touch upon load frequency control or modeling of fuel cell systems. So let us start with the small motivation, and I hope you like it. So let us see. Can you identify these dignitaries on the screen? They are our Nobel laureates, right?
Yes, yes, sir.
And interestingly, the first 2, the top 2 are citizens of British India. Am I right? That
Yes.
is Tagore and C.V. Raman. They have a unique contribution. Raman was technical side, and Tagore was given Nobel Prize in what? Try कीजिए आप लोग.
Literature, sir.
Literature, very right. Literature. And they have a unique contribution worldwide recognized. Then we have 3 Nobel laureates from the Republic of India. And the Satyarthi was given on Kailash Satyarthi. He has done good work on, I think, towards children, if I'm correct. And he was given the Nobel Prize along with a citizen of Pakistan. I'm giving a hint so that you can recognize the Nobel Prize was given on what actions, what activity, or what contribution. Guess कीजिए, please. No? Mother Teresa? Even if you do not recall, you can always find the Nobel laureate Amartya Sen. It was on, yes?
Yes, it was given on finance, I think.
Economics.
Economics.
Economics, sir.
Economics. And this gentleman, Abhijit Banerjee, is also on economics. Recently, he was given few years back. Right. What I'm trying to say, we have total how many? 2 plus 3 plus 4. The number is very limited, 7. And out of 7, the Indian citizens are further reduced by 2. I mean, the Tagore and C.V. Raman, it was a different time. Citizen of British India. Then can you identify this man? You are from electronics. Most of you might be from electronics and electrical, and you would have studied his theorem. Sampling theorem.
Nyquist something.
Nyquist. He is Nyquist. Sampling theorem you can recognize. You may not know the person, but when I say sampling theorem, you might catch it very well. See, the Nyquist theorem or Nyquist contribution, they have a unique contribution. In fact, I really like his contribution in the sense that the lab he has worked in, that lab has earned 6 Nobel Prizes. It is a unique contribution or achievement in the world, I would say. 6 Nobel Prizes were awarded to the lab which Nyquist has worked in. And there are 11 researchers involved for the 6 Nobel Prizes. It's a unique contribution, we must appreciate. It was Bell Lab rather. And his contributions are Nyquist frequency, that is the sampling rate we have been dealing with. In fact, I believe अगर ये sampling नहीं होता तो आप data acquisition और digital electronics में इतना advancement शायद possible नहीं होता. So they have a unique contribution. Then he also introduced the Nyquist stability criteria, apart from Johnson-Nyquist noise. Johnson-Nyquist noise has, I have further to elaborate on. And the other interesting point is Nyquist had 138 patents to his credit. That means अगर वो 30 years का active life ले लें, right? So how many patents per semester you get? $30 years means 60 semesters.
Almost 1 per semester, we can say, like.
Two.
2 is a 2.
Two per semester means every quarter you get 1 patent. And these days we struggle, all of us struggle, because patent has been made mandatory as far as the HAG scale is concerned, and we struggle. The point is, he was able to make every 3rd month 1 patent. But those, yeah, hello? Yeah, please? Anyway. So, I mean, putting a patent every 3rd year, but that was different phase. I mean, around 100 years back or so. So when 70 years back, when the science was developing, in fact, everything was new. Somehow I feel patenting would have been too easy also those days. When these days things are saturating. I mean, new things are coming, and it is difficult I mean, difficult means it is challenging, I would say, to make a patent. But they have a unique contribution. And the C language which we study, C or Unix also, are the product of same Bell Lab. Other interesting point is, you see these 2 publications. One publication is by Nyquist in 1928, and it was published in Physics Review. Page number देखिए आप, page number is 110 to 113. Right, and the title is Thermal Agitation of Electrical Charge in Conductors. At the same time, you have a paper by Johnson. The page numbers are 97 to 109, just before the Nyquist publication. I mean, it is same book, same booklet, I would say, and 109, other one is 110. One after the other. And the title is Thermal Agitation of Electricity in Conductors. They have, the point was, they have same finding. 2 independent findings, same time these were published. That's why you get John Nyquist noise. They had a combined credit to this, because they had the same publications. Right. Yeah, try to find this man. And he is very popular. Can somebody identify? You would have studied Fourier series. I have given a hint. You would have studied Fourier series. That means he is?
Fourier.
Joseph Fourier.
Hmm.
Joseph Fourier. He was the person who has given us the discretization of frequency. I mean, he said that a complex signal can be thought of as collection of sinusoids of different harmonics. So he introduced omega 2, omega 3, omega. It was something like discretization of frequency. And he also participated in freedom fighting. So he was a great mathematician. People used to appreciate, even today, it is said that he has the maximum development has happened the last century. Fourier is the key contributor. Right. Then the last picture, you would have studied or you would have come across fuzzy logic. Those who does research or higher studies, fuzzy logic is, one key component for specifically for the intelligent control. So, can you make out now? Mamdani. He is Mamdani. Right. And Mamdani has studied in India. That's what I picked up it. He studied, I think, somewhere in Pune, if I'm correct. He has 1 degree from Pune. Yeah. He was educated in India in 1966. Then he went to UK. His contribution is the Mamdani inferencing. That allows you to implement the fuzzy logic. So, he has a Indian inheritance, but his contributions are unique as far as fuzzy logic is concerned. Anyway, coming back to the topic. So the development usually, if you do a survey, is related to the electricity consumption per capita worldwide. So the figure shows you the consumption in 2020. So in this picture, you'll find the countries like Norway, Qatar, Canada. They are the highest consumer of electricity. Am I right? And in this list, you do not have India. It will be there somewhere next, but in this list so far, you do not have. And see the position of UK, 4,500. Then US, 12,235. And somewhere we have 972. So our position is here. So, as far as the consumption is concerned, per capita consumption is concerned, so we have very low in contrast to the leading countries. So that shows where do we stand. And the major energy is produced by these components. So in which you have the till to 2030, you do have the estimation, and major contribution comes from which component?
Renewable, sir. Renewable and biomass.
Renewable वो दिखाया है इसने, बट आपका जो मेजर कंट्रीब्यूशन है वो अभी भी कोल पे है.
Yes, it is coal, but by 2030.
Right. Yes. So there are dependencies, and majorly you rely upon fossil fuels, that is coal, oil, natural gas, nuclear or so. And while producing the energy, you look for cost, the safety, disposal of waste or so. This shows you the capacity growth by region or country. In this also you will be, in fact, in this case, we are at a good position, relatively in contrast to other. So, but majorly it is led by China. Right. So, as far as renewables are concerned, you look for reduced electricity bill, lifetime low maintenance, you consider environmental benefits, and those people who are close to Delhi or NCR, they can appreciate the requirement of renewable generation, and of course it has to have a high return. These could be the features you look for, and you can compare the renewable versus non-renewable. So cost, and in fact, apart from cost, what is most important is the side effects in terms of pollution, in terms of the environment. So that is one key factor, and as far as the renewables are considered, so they are better as far as these features are concerned. And also they will have, if you depend upon sun or so they have a repetitive recurrence or daily, so that allows you to take the advantage. and make it cost effective. There could be one-time investment which is significant. You can have direct use, indirect use also. So these things are, I mean, generic in nature, and so that you can use directly as far as heating is concerned. Photovoltaic devices or solar cell allows you to convert the sunlight directly to electricity, and they have advantages. There are issues, of course, issues in terms of efficiency and all. And that is how these days you find, these days on top of the houses or buildings, you find solar panels, and government also is gives the incentives. I mean, if you install panels, you get a discount in your electricity bill or so. So that way it is being encouraged. And you can think in general a complex system where you have multiple power generations, and that is connected to grid for further usage and distribution. So when you start putting these things into place, they have their own challenges also, and that leads to some kind of research. And I mean, when things are put in place, along with having the advantages, they do have their own requirements, and that gives rise to new requirements in terms of research or so. So photovoltaics, as far as this is concerned, there are it has research challenges, and that is in fact in terms of opportunities, cost, or their production, fuel cell. They have requirements of batteries, hydrogen storage, or so. So there are three major contributors: solar, wind, and fuel cell, which is I feel prominent. And solar energy, as far as our country is concerned, we have a good exposure, so we can take the advantage of that. And the government of India is encouraging. They do have in place, or we do have in place, the National Solar Mission, which was launched in 2010 for specific to the solar energy. And we do have targets for in terms of I mean, how much country should produce or so. And this shows you the capacity till 24. It is increasing day by day for different components, and good progress has been made. This shows the building. I mean, daytime you generate and nighttime you use it. So that is the advantage you get. As far as photovoltaics are concerned, of course, it is sun to energy, but there are issues in terms of efficiency. So efficiency, as far as solar cells are concerned, typically see it ranges 4 to 8 for different class, and 12 to 16 or 15 to 18. That means it is lower side. It is lower side. So as far as material science is concerned, that is one area which allows, or which offers opportunity for the researcher, so that it could be enhanced to further. And somehow it is, I think, if you see worldwide, they do have reporting of, but it research stage, of course, 30-35%, but they are not commercially available so far. So there are, in terms of material, there are research scope which one can increase the efficiency of solar cell. And in general, the solar cell can be thought of as producing a small voltage, that is half volt. And half volt, you know, it is very, very small. So when you want to have a requirement of large power, so you either go for a large power or current or voltage, so you go for a series combination, which allows you to get for the higher voltage, or you go for further combination as far as current is concerned. This would be the typical plot of a PV cell. And we notice these power versus voltage, lower curve, power versus voltage. So somewhere you find a point which is which gives you maximum power. So technically, our interest would be you allow, or you force rather, the plant or the solar cell based plant to work at this point. If you design your plant to work at this point, so you'll be in a position to extract maximum power from the plant, from the panel. So that's why the term has been claimed as maximum power point tracking, because issue will be the sun itself is variable across the day. It will have a different radiance that keep on changing. Then you have cloudy, non-cloudy weather. So it is, since it is dynamic in nature, so there will be a challenge to make your plant to work at this point, because this point is dynamic in nature. And how this has been achieved, or so how this has been obtained, that we will deliberate further. So these are, current versus voltage or power versus voltage, typical plots of a PV system. And we have defined here, the requirement is your plant should function at this point so that you get maximum power from the plant or your solar panel. Then this shows the putting the components or the solar cell in series or in parallel, depending upon the requirement. And when you put these series and parallel, what I have shown you, this is say one cell. Let us say it is for one cell. When you increase the number of cells, so you start getting this kind of design. You start putting them in parallel. You start putting them in series, or series and parallel combination put together. If you do so, this plot shows you the PV plot when you have two cells. So two cells in series will give you large voltage, double of the voltage. Two cells in parallel gives you the large current. So that way you start generating the panel. And the issues will be when the panel is placed in under working, then this will be exposed to sun. That is how you convert the sun to electricity. But sun itself has a constraint. The picture here shows you the variation of sun temperature, irradiance and temperature during the day or year or so. So if you see the entire plots are jerky in nature. That means the input is dynamic in nature. Since it is dynamic in nature, your this point is also bound to be affected. So that offers a challenge for to design a control algo so that your plant works at this specific point and you get the maximum advantage, maximum energy of the plant. Typically, the panel or the cell in general, they are categorized by certain parameters, and the figure here, the slide here shows the specific to Kyocera. There's a module called Kyocera, Messrs Kyocera KC130GT module, and they are the 5 parameters for a panel or for a cell, you say. So these are taken from certain data sheet, and the cell working you want to understand so that you can do modeling, you can do simulation, you can do design. So for that you need certain equations and certain modeling. So this is specific to the Kyocera. I'll define these parameters, what these are. But the point is, if you have these parameters, you can characterize your cell. Characterize, when I say, means you can plot your current versus voltage or power versus voltage curve from these parameters.
So what is A here? The constant A value?
Yeah, they are some constants. I'll define it later. Just wait few slides down the line. We'll define. They are the name for like series resistance, shunt resistance. They are the parameters. And A is identity factor.
Yes.
Right.
Yes.
Yeah. So
Thank
we'll
you, sir.
define it later. We'll define it later. And the point is, when you have these parameters available to you, you can start modeling the cell. You can start characterizing the cell. You can see how it functions. What are the variations of functioning under the different sun, different temperature, or different sun and temperature put together, right? So this allows you to characterize. Interestingly, the manufacturer does not give you these parameters. That is the key point one should know. And scientific community needs modeling and control. If you want to do, you need critical study. You need these parameters. I mean, experiments are always not possible, but companies which makes the solar panel, they give you the plot. So the question would be, from the plot, how do you attain these? And that problem formation would be for PV modeling. I mean, how do you get from the given plots or given data sheet these parameters? That forms the problem of PV cell modeling. So for Kyocera 130 GT, specific plots are shown here. So first one is current versus voltage at different irradiance. So the numbers are 1000 watt per meter square to 200 watt per meter square. So 5 plots are generated here, and you will see as the irradiance is enhanced, so your current is also enhanced. I mean, the blue plot is for 1000 watt per meter square sun, or the lower side you have 200 watt per meter square. So the current is enhanced. Similarly, the power is also enhanced, and you will notice the maximum power point. I mean PV plot. So of course you do have everyone, but every plot will have a maximum power point location. But as the sun is increased, the point also is moving upward. So it is dynamic in nature as far as sun is concerned. Similarly, you have their thermal dependency. So thermal dependency, not measured, but it is there. It is there. So these two parameters, G or T, that is sun and temperature, would be the key factor to assess your cell, how it works under different environmental conditions. So, and when you start putting them together, multiple cells or so, or multiple, you make a module or different irradiation or different conditions. So one condition could be they have uniform irradiation, means the entire panel is irradiated or illuminated by the sun uniformly. Of course, it is a rare case, but under this assumption, the plots would be like this, right? And when the sun or G is enhanced, the maximum power point moves upward. And when you have partial shading would be you have suppose certain panels, and part of the panel is having a different V value, say 1000, and part of the panel has say 800, 700, 500 or so. So if you have this kind of cases, you would see the lower plot. The characteristic of the panel would be, I mean, power versus voltage plot would be the lower one. And can you make out the difference between the two in terms of power point tracking?
Sir, there are number of local MPs,
yes.
and in
Very
case
right.
of non-uniform.
Yes, in case of non-uniform or partial shading, the number of peaks are multiple. Number of peaks are multiple. So challenge would be, earlier you wanted to track using dP by dV or so, a point here. In this case, the points are large in number, more than one. So challenge would be to identify which one you want to attain, right? In this case, the maximum power is here, right? We have 3 peaks. So out of these 3 peaks, 2 are designated as local MPP because they are lower in efficiency or lower in power, and this middle one is the maximum. But interestingly, each of the point here would follow dP by dV as 0. I mean, if you we use a small mathematics, you find maximum or minima, we always differentiate the function, is it not, and equate to 0. So in that sense, all 3 would have dP by dV at 0, but the challenge would be to find which one has maximum power, right? So that I'm citing the challenge which the partial shading would offer as far as research or development is concerned for partial shading, right? I
Sir-
hope you got the message. Yeah.
Sir, the patterns for local MPP or global MPP, all are having the same pattern because of
Yes.
DP by DV.
Yes,
Yeah,
that
variation.
factor is uniformly applicable dP by dV 0. So
Ah,
that's why
yeah.
I'm saying you have 3 points here. But challenge would be which one is of interest to us. Our interest would be global. So you'll find if you do a survey, you'll find as far as partial shading is concerned. So typically they use the optimization techniques to find a global maxima. Is it not? See, when you have multiple maximas, the concept used is optimization. Optimization techniques might help you to find a global maxima. And that advantage you can take as far as attaining a maximum power point tracking is concerned under partial shading. I have one paper presentation which will down the line, which will tell you how do you find the global MPP using deep learning. I introduced a brief discussion on that, right? But let us get convinced. For uniform shading, the challenge is not as great as partial shading. And partial shading is such a condition you cannot avoid it because it is environment. It keeps on changing. It is dynamic. It changes right from morning to evening. Is it not? So if you do a survey, you'll find lots of publications on partial shading or MPP under partial shading. That is one way is theoretical. Other one is if you do experimental, then you need to have some kind of setups which would be able to track the MPP at runtime. That would be challenge. I mean, your sun would be like you have a cloudy weather, you have peak hours, like Delhi you take the winter, you have different working, different environmental conditions. Summer you have different, so there's a huge change in terms of temperature. There's a huge change in terms of exposure of the sun. So those things also would become interesting as far as research is concerned. Yeah, so since now I have introduced the cell in general, so let us go to specific cases. The first one, I'll take the modeling of a PV cell. What modeling means and how modeling is done. So that will help you to, if somebody wants to take up this work further, to help them what modeling is. So the parameters which we have used earlier, these one, there are two types of model. Usually the PV cell is used to describe. So the first one is a single diode based model. So here you have 5 parameters. How many? Total 5 parameters. That means these 5 parameters can describe functioning of a cell. And when you make a module, that number of cells would come into place in series and parallel. You get other parameters. I mean, number only would come, additional component. But essentially, these are 5 parameters as far as a PV cell is concerned. That is to be modeled with the help of a single diode based PV cell model. And you do have the other concept of double diode. Triple diode also, few papers are there. But double diode, if you use the number of parameters are how many? 7. 7. 2 parameters are introduced, 2 additional parameters are introduced. That is IO1, IO2, right? Or A1, A2, right? So when we say modeling means the plant or the module or which you have, you are desiring to model. So you might look for to describe that characteristic of the plant or the panel with the help of 5 parameter base, that is single diode model, or you may go for double diode. Interestingly, the double diode is bound to be more accurate. It will describe the functioning of the panel precisely in contrast to single diode model. But it depends the kind of accuracies you are looking for. It depends the kind of effort or the computing power you are having. But nevertheless, both can describe the functioning of a PV panel. These are the dependencies like on temperature and standard equations, nothing new, on temperature and sun, that is G. And if you have other parameters defined, so you can start plotting the characteristic of the given model, given panel, right? So they are typical constant which are, I think, very well available, their numbers. But the equation which connect the current, right? Current versus voltage, because I'm looking for a PV plot. PV plot means that is VI plot or PV plot. So if you look for current versus voltage, so this is the voltage and this is the current you get, right? So this equation, interestingly, some of you, if you would have noted, you see here also you have current, am I right? This is also current and this is also current, and this is also current. What kind of equation these are called when you have a X dependent on X? क्या बोलते हैं इसको? Yeah. See, I want to plot the current versus voltage. Voltage I will start varying. If I vary the voltage, I must get a current, right? But current itself is a function of current, is it not? So there's a challenge, small challenge available here. How do you solve this kind of equations? Using?
So we should expand the exponential, sir. We should expand.
That does not help. That approach people have not taken. If you expand it, still it will be dependent. That depends upon the expansion is always applicable when you have a small number, right? So that you have a convergence.
In the other way, like we can take the logarithm or some approximation, sir.
But that is one way to do it. Other way could be there are mathematical techniques. Mathematical techniques are there, like Newton-Raphson method, which you would have studied in mathematics.
Yes.
That could help you. I think Newton reference method that allows you when I is a function of I, that helps you to, it does some derivative and all. It allows you to have a, I forgot the name. There's a technique. This equation is given a specific name when I is dependent on I. I think transit कुछ होता है, transient नहीं, transit equation ऐसा कोई term होता है. I have to see. But the challenge I'm indicating, challenge is the current itself is a function of current. So you have to have a mathematical technique which would allow you to help it. The idea is I want to plot I versus V. So V, I can vary. V is variation of V or open circuit voltage is given in the data sheet. So that allows me to have a range of V. So once I have a range of V, I can start V, like V starting from 0, then delta V or so, and I get different current for each of the V. So I can plot it, and when I make a PV, so V and I will multiply, and V already is varied. So I'll have PV plot. So IV and PV plot could be generated from here. As far as modeling is concerned, the idea is to, from the given PV plots, can we find those 5 parameters? And those 5 parameters are here, see, A, RSH, RS, the parameter which we have defined here, we are using in the equation. That means they are the modeling. They are the parameters which allow the modeling of a cell, characterization of a cell. So once you know these 5 parameters, almost everything about the cell functioning, you know it. So that is called modeling. Similarly, you will have 7 parameters for double diode based model. And dependency of the current, since you have 2 diode here, that is given here. Right. So the modeling is could be done in 2 ways, either deterministic or heuristic. So heuristic means you look for mathematical algos or so. Deterministic means you look for mathematical
Sorry to interrupt.
Please.
In the previous slide, you have written that the parameters are not provided by the manufacturer data sheet.
Yes. But they
And-
provide you the characteristic plots.
Okay.
Since the plots means with the plots like this, which I have shown you, ye wale. These plots mean what they do is they make the panel and they do the measurement on the panel. Right. So once you have these plots, so I look for, as far as modeling is concerned, I look for finding these 5 parameters which will generate the same plot. Got the message? I do a mathematical processing so that I get these 5 parameters which will reproduce these characteristics of a specific cell. So that means if I'm able to match to a good extent of overlapping, or say accuracy are as low as -6 or -7, 10 to the power. So you can claim that you are able to find the mathematical model of the PV cell under consideration. Am I right? Yes.
Okay, sir.
So how this could be
Yes,
done?
sir.
This could be done with the help of the 5 parameters, and in this case, see, I define a function that is ye kya hai ye? This is nothing but the equation which I had. Current is a function of current. So this is, I mean, if I can find the values of these 5 parameters, which gives me this function as 0, it is I minus, what I have done is I have done right hand side minus left hand side should be 0. Ideally, it should be 0. So this fitness function can allow you to find the accuracy of your identification or what you say, modeling of the cell. And similarly for the double diode. So what we do, we try to optimize this fitness function or reduce this fitness function. So once you do it, then you can claim that you are able to attain a good model, provided the fitness function ideally should be 0, of course, but you cannot make 0, you'll make 10 to the 5, 6 or 7. And you have different capability of different algos. So we have tried one experiment. We tried using there's a technique called evaporation rate water cycle algo. It is an optimization technique. We tried maybe some 5-6 years back, or I think 2017, 7 years back. So we tried to use this algo for modeling of the PV cell. And the result, I'll share with you how it is implemented and how the modeling is attained. So, and the other question could be, why did you choose this optimization technique? Is it not? There are a number of techniques available, but the idea was that time it was recently introduced those days, and it was claimed to be efficient to its counterpart. So we thought we should apply this to modeling of a PV cell. And other interesting point was this algo had only few parameters as a tuning parameters. So the work was not much in contrast to other algo. So we preferred this for the global optima. So it has the name is evaporation based evaporation rate water cycle algo, or WCA popularly it is called. So I would say it hereafter the ERWCA. It's a popular technique, and it has only two parameters to be optimized. That one was D constant and NN, D or N constant. So we optimize first for the PV cell these two parameters, so that you get you have to fit this parameter first so that you are able to attain a specific convergence. So you see in this plot, if you vary the D or N, you'll see somewhere where the circle has been indicated, the error function is almost minimum, although the same level. So we have taken these values in this zone for the different for the two parameter, that is number of C's and rivers. These C's and rivers, since the algo is on evaporation rate, so these are the parameters defined for the algo, specific to the algo. So we optimize the parameters of the algo itself, then we implement it to find the optimization for fitness function. And what we got it, these 5 parameters you see here, this is 1, 2, 3, 4, 5. These parameters are plotted in terms of their value versus iteration. Iteration means as the algo is implemented, as it progresses runtime, so we record the values of these 5 parameters along with the RMSC. When I say RMSC means it is nothing but this parameter. This is RMSC, right? And see how it is defined. It is defined as ideally it should be 0. Ideally it should be 0. I mean, if that function I'm subtracting from itself, so I must get it 0. So you would notice here the RMSC beginning it was something like 0.06, and as you progress it goes close to 0. I cannot say 0, but it is close to 0. I mean, it would have been somewhere 10 to the minus 5, minus 6 or so. So in that sense, this algo was able to extract the 5 parameters, so the required 5 parameters of the PV cell to a good accuracy. And also what one can notice, as the RMSC tends to 0, the other parameters are saturated in terms of, means you do not see a change in these parameters, they are constant as you progress along the x-axis. That means there's nothing much to be improved. It is not jerky. Since there's nothing much to be improved, so these solutions beyond say 150 or so onward, they are reliable. They are the solutions which you are looking for. Are you following?
Yes, sir.
Yes, sir.
Great. So this allows you, this mechanism allows you theoretically, how do you extract the modeling parameters, or how do you model the PV cell from a given PV plots, or from a characteristic plots given by the manufacturer. So that is one problem, PV cell modeling. This shows you for the same cell, which has been, I think it was Kyocera 130, if I'm correct. Yeah, this cell, this is your, once you get the parameters, you can always plot the same plot which the manufacturer has claimed. So this is like you see, experimental data versus computed data. Computed is my algo, experimental is claimed by the manufacturer. You would see here, they are in a good match. They have a fairly good match. I mean, the magnitude on the y-axis of the current, it is same as, similar or very close as experimental data. That means modeling is can be claimed to be of good accuracy, reliable. Right, that is IV plot. Then you have for a specific method, if you want to claim superior, you have to compare with the other method also. In this case, we compared 1, 2, 3. I mean, the proposed was the WCA, and it is compared with 1, 2, 3, 6 more. So 6 more is there also popular one. ABC is Aunt B colony. Then you have CSO. MABC, Go TLBO. TLBO is teaching learning based algo. But interestingly, you would see here the performance of WCA is either similar to these or better, because 9.8602, then 8602, then others are little more. So the performance of WCA, which we wanted to use, it is either similar to the claimed one, other techniques, or better in terms of RMSC. That is for single diode cell. And these are the other parameters. This what has been obtained, the in terms of the 5 parameters which we want to extract from the plots for each of the techniques which has been experimented. I mean, you'll find they are similar. I think in this case, you see the factor, the alpha A factor, ideality, 1.48, 1.4812. There are different. There's a difference of decimal, third, fourth place also. But once you plot it, it will have a large impact on your characteristic. So it depends how accurately your method is able to extract. What I'm trying to say is the decimal place difference will be minimal, but it might have a large difference in terms of RMSC, because the number of points are more there. And other parameters you look for RMSC, I mean the fitness function, the MAE, that is mean absolute error, or NFE. NFE would be the number of function evaluation. During the process you are trying to extract your parameter, how many functions, how many F you have computed for a specific method. And in this case, you see here you have 8,000 number of functions evaluation. In contrast to others are 10,000, right, 15,000 or 35,000, even 50,000, sorry. So it is PSO, modified PSO. So in terms of effort is computation. So you save as far as this is concerned, while it is giving the accuracy either at par or better. So that means the technique would be worth implementing as far as the PV cell modeling is concerned. Then this is for double diode. Double diode means that let's say 7 parameters. Similar line, you try to on the same line, you try to implement the only thing is the number of parameters are enhanced and the accuracy of the DD means double diode model would be better. So this shows you the A1, A2 here and RMSC here. As far as look and feel is concerned, it is similar to the double diode, the single diode. Only thing is the equation will be different and your precision or the implementation will be also be different. So this shows you the characteristic. One can generate IV characteristic also. Comparison of double diode model with the other prominent optimizing techniques and their result. So that was for Kyocera. This is you apply these techniques on different modules. So this is photowatt. I mean, you have a technique. The technique in terms of technique 1, technique 2. Technique 1 is for in terms of optimization technique. You have WCA, PSO also that you try. Or once you get a technique in place, method is perfect, then you go for different modules, PV modules, so that you want to know whether your method works on uniformly on different modules also to make it generic. So that was Kyocera. This is photowatt. Specific module is photowatt 201. So in this case, once you apply, you can generate these plots, and if uniformly you get better accuracy, so you can claim a method to be publishable, which is generic in nature in terms of it is applicable to different photo modules. It is photowatt, and further you'll experiment in terms of different temperature. So same module, if you change the different temperature, then you see how this would function. So in this case, it is 75 degrees centigrade, 50 degrees centigrade, and 25 degrees centigrade. In fact, the idea is to make it generic in terms of you have all the parameters, whatever variable. To explore your technique for each case and claim or look for their feasibility. Does it work uniformly everywhere before you start claiming? So this is for different temperature for a specific Kyocera 200 module, and you'd see that the red line and the blue dot, they have a fairly good overlap that allows you to rely on your technique. That's what you can keep on changing the modules. You can keep on changing the sun, change temperature, and explore each one. So I hope I'm able to convey how the cell modeling is done, right? And if you want to have more detail on this, the paper was published in a journal called Swarm and Evolutionary Computation. That time it has an impact of 3.8. Now these days it has something 7.8 or so, if I'm correct. So if you are interested, you can look for this paper. And interestingly, since most of you might be faculty, I would like to tell you something more as far as the team is concerned. Let me know. I'm hopeful that I'm audible and the people are listening.
Yes,
on the
sir.
side.
Yes,
Yes,
sir. Yes, sir.
So
Sir,
I have
you're audible, sir.
great. See these three first members, Dhruv and Pallavi, they were my UG students. I'm not sure in this team do you have a UG students, but I believe you have other faculty or PhD scholars. But my team we had Dhruv, Pallavi, and Ashish. They are the 3 UG students, final year students, and then we have myself and my colleague Dr. Vineet. Interestingly, Dhruv was so intelligent, he made 5 publications. And I repeat, 5 publications. See, 5 publications for a BTech fellow is a very good achievement. And you will find this kind of cases rarely happening in the,
Yes.
I mean, rarely. And he
Yes.
made 5 publications.
You are
And
right,
later-
sir.
yeah, and later he moved to for masters to McGill, Canada, and he has done a master from there. Right now, he works for a company called OpalRT. OpalRT is into real-time hardware. Some of you might be using, which allows you to put your MATLAB code to real-time hardware. You want to check whether it will work in real, very high speed switching also involved. So that is the. I mean, we really enjoy the working with this team. All of these 3, Pallavi and Ashish, they also moved to US and they did master. Now some of these have moved to machine learning. Then I think Ashish has gone to robotics, if I'm correct. So that's what. But we are proud of the team. And interestingly, they are UG students. UG students will be busy with their qualifying 5 courses per semester. They were able to find time. They used to sit in the lab day and night, and he was able to make a very interesting paper on modeling. And the work was very well appreciated by this journal, Swarm and Evolutionary Computation. So as far as this audience are concerned, I believe they get the message what modeling is, how modeling is done, and what is the meaning of modeling, how many parameters are involved, what are the parameter tuning as far as optimization techniques are concerned. And this specific work was on evaporation rate based water cycle ENBO. So that is part 1. I hope I'm able to convey. The part 2 is on controller, right? So controller, as I have indicated to you already that efficiency of solar panel is typically in this range, 9 to 17%. And efficiency of a DC-DC converter is typically the 90% or so. So you need to extract the, you have to force the cell to work at a point where it offers maximum conversion, maximum efficiency, and challenge is to make it there. You have to have algos in place. And why do you need algos? That also I'll introduce. So it is something like, as far as usage is concerned, you have a PV cell, you have a current or voltage available here, and you have a load. Right. So my query to audience would be, can I use my PV cell directly like this? I have a voltage source and I have a load. A load would be your, depending upon your requirement. It could be something like a water pump. It could be domestic appliances. So we do not use PV cell like this. Directly, we do not connect the PV cell to the load. What is the reason?
Sir, output is DC, PV source key. And
That
to,
is okay. But even if
to lower down the level, this converter is used, DC to DC.
Inadequate power. Sometimes you can have more power and less power, so you want to track a maximum power. So in order to meet the load demand.
You have a point, but the major issue is efficiency. You have to see the impedance of panel. Is it not? the loads are designed for a specific power rating or current rating, right? So we never connect the load directly to cell. Even if you are able to make multiple cells in parallel and series and you get a required voltage or power, even then you will not connect, because there's the impedance offered by the source, right? That is one thing. Efficiency you cannot get. You know, we had studied a maximum power point theorem. What theorem says? For the maximum power point transfer, you need to have what?
So load impedance resistance should be equal
Yes.
to
Yes.
internal resistance.
Yes. तो ये मैचिंग इसमें नहीं बन पाता, ये मैचिंग इसमें बन ही नहीं पाएगा. जब मैचिंग नहीं बनेगा तो आपकी एफिशिएंसी नहीं बनेगी. That is the, I would say, blunt answer why they are not connected directly. So to bridge the gap, you need to have a DC-DC converter. ये load balancing का ही काम करता है, so that you are able to, and through that process you are able to attain maximum power, right? So अब क्वेश्चन ये आता है कि once you have a DC-DC would have a design and it would have a switch. If this is a typical DC-DC, it will have a switch to be operated. So you need algo, you need some kind of mechanism which allows you to operate this switch and provide the load balancing between load and the source. So for that, you need a technique called, you need the maximum power point tracking technique called MPPT algo. So this algo is to be developed so that you get maximum power from the cell. And the problem formulation is maximum power point tracking algo. Yeah, please.
Sir, जैसे आपने, you have told that the efficiency of this PV cell
Yes.
is
Yes.
9 to 17%.
हाँ.
Sir, that is without MPPT or
नहीं,
with
इसका अपना,
MPPT?
इसका अपना इंडिपेंडेंट.
Self without MPPT.
ये जो, yes, जो फोटो सेल हैं उनकी एफिशिएंसी बहुत कम होती है.
Yes.
बट वो जो whatever efficiency you have, that should be transferred. वो भी नहीं होगा फिर. Every component will have its own limitation. So to get the maximum benefit of the cell, right? To get the conversion from what जो आपने convert किया है, that should be passed to the load. तो तब जाएगा जब आप load matching करेंगे.
So how much it
is
increased, sir?
improved, sir?
How much it increased, sir?
आएगा, आगे आएगा ना. जल्दी क्या है? अभी तो टाइम है हमारे पास आधे घंटे का. टाइम है नहीं? We have till 7:30. So अभी तो क्या बजा? आपको जल्दी तो नहीं होगी, I believe.
नहीं,
No, sir.
हाँ.
No, sir.
So and I hope you are also engaged also.
Yes, sir. Yes, sir.
आप अकेले बोल रहे हैं सर?
All are engaged,
Oh.
sir. So we
All
are
are
eager to
engaged.
learn that.
आप वो
Yes,
All
sir.
are
Yes,
enjoying,
sir.
sir.
हाँ.
Yes, sir.
If it is so good, I would say. क्योंकि आप
Sir,
बैठे हैं
can I ask one question, sir?
please.
So you told that in order to transfer the efficiency from source to load end,
हाँ.
we are doing this MPPT algorithm.
Right.
Okay, sir.
Right.
But normally it was seen that, sir, the voltage has been adjusted. The output voltage of the SPV, which is stored in the battery, it has been adjusted with the help of the DC-DC converter. Understand? So in that case, normally what I saw that the efficiency, there's a very minimal change in the efficiency.
नहीं, इसको let me show my result. वो 90s में आ जाएगा.
ठीक है सर.
हाँ,
सर
90s
वो
में आ जाएगा.
जो वोल्टेज की बात कर रहे हैं ना, for that correspond to maximum power. That
Correct.
is, I think, same in all the cases.
Correct.
But P max is different.
Correct. That is true. That is true. You play with the balancing, and I'll show you how you attain. Give me 5 minutes more. So I will take you to the plot and leave you at the dp by dv at 0. Then you'll be convinced it has been done. Right. Anyway, so that is how the connections would be done. You'll have a DC-DC, then you have a MPPT algo. This side your cell, and this side your load. So we tried 2-3 work, and probably one I can share with you. So DC-DC also you can have buck boost or buck depending upon the requirement. So I'll not go into detail of the. You can try small numerical also. I mean, this kind of questions could be generated as far as teaching is concerned. And for MPPT, there are n number of techniques available. It is also, in fact, I would say fairly matured area by this time. And you have, basically, you'll have, as far as uniform sum is concerned, uski technique alag hoti hai. As far as the partial shading is concerned, uski technique थोड़ी सी और भी complex होगी. But you have a issue that you need ultimately, at the end of the day, a good MPPT controller or tracker. आपको चाहिए. So we have observed in the plots earlier shown that you have a dp by dv 0 when you have at MPPV. So we get this clue that somehow this could be useful. This could be useful in the sense if I differentiate dp the PV plot, that is dp by dv, it is free from environmental conditions. Am I right? Since the PV plot would be function of G and T, but in any case, the dp by dv is always 0 at MPP. So that gives me some kind of reference we can always trust, because in control you'll have reference tracking. So my reference is known to me. So that helps me to locate my PV plot maxima. That is one thing. Second thing is the algo which you want to make, it should be cost effective. I mean, you cannot start putting large number of components and costly hardware and claim I have made a good technique. In contrast, you should have a cost effective technique which should be easy to implement. In contrast, if you compare with AI based techniques which needs large computations, costly hardware. So as far as implementation is concerned, that should be avoided, I would say. And you see the best option comes to PID. PID control. PID is it is as old as James Watt engine, so it is well trusted, time tested technique. And PID, if you can incorporate in your control algo, so this should be preferred in contrast to other AI based or complex algo, which is compute intensive or difficult to tune or so. PID, the tuning techniques also is known to you, and it is simple to implement. Only 3 small components you put together, then you have controller in place. And as far as testing is concerned, you test your algo for irradiance when you vary G at a different G level or different temperature, or you might vary both together to critically see whether your algo is working or no. So first algo, which in fact we had a small publication that I'll share with you. We tried the application of a fractional PID controller on to track your MPP. Fractional PID controller, wherein the fractional part is implemented with the help of a popular technique known as OSTA loop. It can be implemented in S domain, or this is specifically S domain. You do have Z domain techniques, which is GL. There's a technique called GL algo. So that could be tried. But we tried in this work, we tried the fractional PID controller. And you know when you implement something, whether the performance is up to the mark or so, you need to have some kind of performance criteria. So the criteria were power loss, actual power minus experimental power. I mean, this should be minimized. Relative power loss. You define few parameters as far as the efficiency of the algo is concerned. So that was the assessment criteria. And performance also could be evaluated in terms of undershoot. I mean, you want to have a power, specific power. So if you are able to attain that power, fine. Otherwise, it will be lower. So lower means maximum undershoot should be avoided. And your algo cannot take longer time to attain your desired point. Ripple means the variations in the power during usage should be minimized. So these 3 could be the other performance criteria. And this is what it is. You have a PV source here, then you have a DC-DC converter and a load, right? So we pick up the voltage and current from the panel. It is measured here. And from these you compute the PV plot. And the set point is dp by dv has to be 0. That is I would say it is more of a universal set point, because every PV plot will have dp by dv at 0. So idea was to attain this set point. So this is your set point. Then you compute the error. I mean, it sets points from this set point how you are how much you are low. You cannot be above the set point, because set point is the maximum power a panel can fetch to you. If it is 1000 watt, you might get 980, you might get 960 or so, but you never can get 1020, because the maximum capacity of the plant is say 1000 watt. So that's why I have mentioned here undershoot. Overshoot का इसमें scope ही नहीं है. These are the power generating devices. Then you have a controller. This information given to controller. The controller will generate the control signal or V reference, which is given to the pulse width modulator or PWM generator, and you control the DC-DC switches here. So that forms the control loop. And this we tried, and popular other to know your efficiency of your proposed algo, that is fractional PID. So you usually compare with the other algos. So in this, the classical technique was P&O, you perturb and observe. You can compare with that, or incremental conductance. So these two plus the proposed one could be compared. Since you have the fractional PID, that will have 3 gains of PID controller and 2 alpha beta constants of the integral and derivative. So you have 5 parameters to be tuned. Since the tuning, the large number of parameters, we try to use for tuning the Gray-Wolf optimizer. It is a optimizing method or technique which is established, I think, maybe 10-15-year-old by this time. So these 5 parameters we evaluated with the help of GWO, and the list is given here. Right. So, and the performance was you get you have to, I mean, when you optimize in the fitness function, so to minimize the fitness function, so that you are able to extract these 5 parameters. This figure shows the integral time absolute error versus iterations for this plant, right? In case of PID and fractional PID. So you would see the number is almost similar. This is 1.0, lower side I'm saying 1.066. So it is for fractional PID here, and you have 1.06. I mean 06 or 07, it is visually similar, but they have a large impact in the performance, right? So to test it, the panel was subjected to a variation of profile, environmental conditions. So the output was this. I mean, when you vary your parameters and you look for the performance, so this is performance. Parameter variation is, I think it's not given here, but the performance is when you have a variation of G, so it goes, we have given a G profile, G versus time profile to the panel after optimization. And you would see here the plots and plots. Yeah. So in this case, you would see all 3 controllers along with the proposed one at this small window. It is magnified view lower side. So the proposed one is dP by dV technique using fractional order PID, that is black. So the black has a performance variation like this, right? In contrast to the other technique which are classical or the PID, conventional PID, so you would see the variations along time offered by the fractional PID is minimal as compared to the rest 3. Am I right to say?
Yes, sir.
So
You
that
are-
shows you are able to attain a good control algo. You are able to implement a good control algo, and or other way to say is the fractional order PID has a superior performance in contrast to the classical P&O and IC or dP by dV using PID. Interestingly, the tuning of PID also is done with the help of GWO and with similar conditions, of course. Otherwise, you cannot compare. That is one thing. Second thing is other point. This was a uniform shading here, right? I mean, G remains same from say point this time to this time. Or if you go for variation of G with time, you have a ramp here. But during the ramp operation, when means G would have gone from say 1000 to 800 in a specific time. So during ramp also, you would see the variation of the fractional order control scheme is minimum as far as this is concerned further. In this case, it is also minimum in contrast to the other 2. So overall aggregate performance, अब जब आप RMS निकालेंगे और so, you will find the validity of fractional order still holds good as far as the variation or the ramp upper to lower is concerned. And like this, you can find several points, several important points, like in this case, growing up. The growing up, the black one is still, what I'm saying is still valid here also, right? And the red and blue, they have maximum variation. That's what you can expect from a typical classical technique, that it has limitation. So these are the numbers, shows you. The efficiency would be in this case, it is 99%. In this case, efficiency is defined as, I'll have equation for that somewhere. Yeah, relative energy loss, improvement, decline, power loss. I think efficiency, I missed it. So it is basically, it will be in terms of power, input to output, what has been fetched by the load. So it is 99% in this case. And other one is visually they appear to be far away, but even this is 97%, right? So 97 to 99, you have 2% advantage. But as far as power is concerned, did you say throughout life, I mean its life, so it will be a significant cost saving. This work was published in a book chapter, and interestingly, the team is same. So it was, I think, if I'm correct, it was Elsewhere book chapter, right? So shall I introduce one more? We have time.
Sir,
Yeah.
the analysis you have done
Right.
in the previous slide,
Please,
at the leading and trailing edge also, is it must to do the analysis on these parts?
you should do it, because see, the maximum to assess your scheme, one way could be you take a aggregate one number from here to here. But during the transitions, I mean, when you have a ramp of G going or coming down, that gives you dynamics of the plant, how your control algo is able to cater. So it is recommended that point should be looked into.
Okay, sir. Thank you,
Because
sir.
otherwise, the expert can ask you. I mean, if you are looking for a good publication, good means a reputed publication. So you have to claim, you have to show your technique is superior in different environmental conditions. The conditions kahan se aayega? Condition aayega when you vary G, G might grow, G might reduce. That will create a ramp. When people do it with students head also. So I would recommend it should be done several points, so that there is no scope of ambiguity. I mean, to claim a technique to be generic in nature, the number of experimental points has to be more, so that you are able to generate a table or so and convince the expert team that the claimed algo is a good one, acceptable.
Thank you, sir.
आप क्या कर रहे हैं? आप I mean faculty है, student हैं?
The faculty.
तो आपको तो करने ही पड़ेंगे.
Sir,
You do
I
not
have
have
one
choice.
question.
Please.
You have shown the response at different temperatures.
टेम्परेचर जी पे भी होगा, सब पे होगा,
अच्छा,
सब
Sir,
पे होगा ये. हाँ.
have you optimized the temperature at which the panel will give maximum output? Because when we increase the temperature, output decreases.
वो रिड्यूस करता है, सिग्निफिकेंट नहीं होता बट रिड्यूस करता है जनरल.
Have you done such research that this is the temperature at which this
This should be
will give the maximum efficiency?
right. You are looking for आपका क्वेश्चन उल्टा हो गया कि इस पैनल को इस टेम्परेचर पे यूज करो तो आई गेट मैक्सिमा का मैक्सिमा.
जी जी.
We in this case it was examined for different temperatures, and probably if you make a table of all those, I mean normally your temperature like Delhi would vary, say typically could go from throughout the year, say I mean 10 to 50, right? One can do it if you average with a step of 5 degrees. If you find the values of all and then make a table, you can always get the number.
Okay.
निकल आएगा number. I don't see any issue. I mean, once algo is in place, you have to change the number, nothing else. But वो list में हमने नहीं दिया है, यहाँ पे नहीं है.
जी.
Okay, so I think I have few. Shall I continue?
Sir, one more basic question, very basic question.
पूछिए.
Sir, we are saying that the consumers who are using this rooftop solar panels are getting benefits. What kind of benefits they are getting?
Yeah, I'll tell my case. In our university, we have installed these panels on rooftop. Okay. And government has given some 10% discount on the bill. I mean, the annual bill of electricity what we get a discount of 10% on that. And when you have a large consumption, it is significant. वो लाखों में जाएगा.
एक सर जब हम 3 किलोवाट का कोई सोलर पैनल इंस्टॉल करते हैं ना सर,
Right.
तो उस पे 78,000 का
Correct.
सब्सिडी
Subsidy भी है. Subsidy is given in terms of installation.
यस सर,
But during the usage over the period of 10-20 years, you get a discount also additional.
यस सर, यस.
So, and apart from that, the place we are sitting, we do not have air to breathe.
ओके सर, यस
So
सर.
we must go for it. You do anything or everything you do it which save the lungs of your kids, I would say. And
Yes.
all of us, most of us, I would say, might be from NCR. And this problem of population, it is not only NCR, it is of North India, I would say.
जी जी सर.
हाँ, आप कहीं भी निकल जाएं, हर जगह ये दिखता है ब्लैक.
यस सर, पूरे एनसीआर की दिक्कत है सर ये.
And not only that, human beings are very sensitive. अगर आपको दिन में सन दिखाई न दे, आप gloomy रहते हैं.
श्योर सर.
आप कंफर्टेबल नहीं रहते. तो clean sky is the need of the hour. So government is putting effort, but government alone cannot do. Each of us. I mean, आप बाजार जाएं and people quickly pick up the items with polythene. So that is also, if each one of us do our duty, probably you can start seeing the effect within 6 months. लेकिन आधे करते हैं या आधे नहीं करते तो उसका चेंज नहीं आता. वहाँ पे इशू है. जो लोग एजुकेटेड टीम है, जो एजुकेटेड कम्युनिटी है, इवन वी डू नॉट डू इट. we assume कि ये हमारा काम ही नहीं, गवर्नमेंट का काम है. गवर्नमेंट क्या करेगी? गवर्नमेंट कैन नॉट गो टू ईच हाउस एंड गिव यू ऑक्सीजन सिलेंडर. दे कांट गिव. वो पॉसिबल नहीं है, लार्ज पॉपुलेशन. सो लेट अस स्टार्ट. जो आपका कंट्रीब्यूशन है माइट बी स्मॉल, बट वी मस्ट डू इट.
This subsidy varies or it is fixed कि इतना करेंगे तो इतना मिलेगा, ऐसा?
कमर्शियल, मैडम, ये कमर्शियल एस्पेक्ट है. हम लोग कमर्शियल में हमें इतना नॉलेज नहीं होगा, बट गवर्नमेंट सब्सिडी देती है, इसमें दो राय नहीं है.
Okay, thank you, sir.
One can explore the different agencies अगर आपका इंटरेस्ट है.
But sir, at the end, if we cannot improve the efficiency of solar photovoltaic, आप सब्सिडी कितना ही मिल जाए, but that is will go beyond the budget of the consumer, sir.
Yes. अभी भी जो कमर्शियल प्लांट आते हैं, they are not tuned for MPPT.
Yeah.
वो क्या करते हैं? Yes, वो इंस्टॉल कर देते हैं जो भी कंपनी का डिजाइन है, because environmental conditions you cannot forecast.
कॉस्ट भी इंक्रीज हो जाता है उसका. वो दोनों चीजें देखना पड़ जाती हैं वहाँ पे.
Yes, but in fact, interestingly, I had my MTech boy who was working in solar power installation. I met him one day and then he said, I just asked, मैंने कहा MPPT कौन सी टेक्निक लगा रहे हैं? सर ये MPPT कुछ नहीं होता, हम वहाँ पे बने बनाए आते हैं, इंस्टॉल कर देते हैं. वहाँ पे इशू है भी, चैलेंज है. Or might be they are implementing it pre-tuned, pre-trained, something like a PID or so they might put in place, some small algo, but वो efficient नहीं बनेगा. अभी तो evolve हो रहा है, ऐसा है.
So I have seen that अगर solar photovoltaic आ रहा है, बैटरी के साथ वहाँ पे चार्ज कंट्रोलर होता है, that itself वहाँ पे एक इनबिल्ट MPPT कंट्रोलर रहता है सर.
Yes, वो रखेगा. I mean, अगर सिस्टम चलाना है कुछ रखेगा, बट वो सिग्निफिकेंट है नहीं है. That is what the academics would look into. Or whether there is a scope of improvement of the same existing one further, वो स्कोप रहती है, ऐसा. So shall we continue or
time is over, sir.
Sir,
I need your permission.
We will have your one.
Yeah. Hello.
Hello.
Yeah,
sir,
please.
am I audible, sir? It is really interesting, sir. We will definitely plan one more lecture based on this one, sir.
चलो ठीक है. So I must thank you, and some of you were really encouraged to interact. So thank you once again, Afan.
Thanks a lot, sir.
Yes, sir.
Yeah.
Good evening, Rana sir. Sandeep Rangi this side.
Yeah, please.
Session was very interactive and load frequency control वाला part रह गया
रह
sir.
रह गया है, रह गया. Actually, you time ऐसे रहता है बस. लोड फ्रीक्वेंसी पे तो इनफैक्ट डॉक्टर आर्या बहुत काम करते हैं, तो ये हिमसेल्फ
Yes sir, actually
हाँ.
मैं सर के साथ ही काम करता हूँ,
बस
तो
बस
I was eagerly waiting for that portion to cover.
आप इन हाउस कर लीजिए. इन हाउस
If you-
डॉक्टर आर्या से अच्छा आदमी नहीं मिलेगा आपको उसके लिए.
Sir.
You can come to the Mr. Dr. Sandeep. You can come to the JC Bose University. We can work on that part.
We will invite you, sir.
Right.
Okay.
Okay,
So, sir,
thank you, sir.
yeah. So it's just a formal wind up of this session, sir. So I just want to know if is there any question from the participant side? Any more questions? Although it was the continuous question and answer session during the whole session. So I'm expecting if any question left from the participant side, please let me know. Okay, fine, sir. So, sir, on behalf of Department of Electrical Engineering, JC Bose University, YMCA, Faridabad, I, Dr. Abhinav Saxena, in the assistance with Dr. Yugandhar Arya, would like to extend our sincere thanks and gratitude for insightful and engaging sessions. Your expertise, clear explanation, and real-world examples greatly enrich the learning experience of all the participants. Your talk has undoubtedly inspired new perspectives among all the faculty members and research scholars, sir. Thank you so much, sir, once again for your contribution for the successful of our FDB. Thank you so much, sir.
Yeah. Thank you, all of you, and good night.
Sir, can we have a group photograph, sir? Rana, sir,
Yeah.
So all the participants are requested, please switch on your camera for the group
You need
photograph, please.
You need a proof.
Yes, sir.
Yes, ले लीजिए.
Yeah, sure. Kashika, please take the snapshot. Kashika, are you there? Okay, no issue. I'll take it. Just
वो आप ही
give,
कर
me,
लीजिए. हाँ.
give me a second.
Sir, I have taken.
Okay.
Great.
Okay. Thank you.
Thank you,
So,
Rana, sir. Thank you so much
Thank
for
you.
giving
Thank
the
you, all
valuable
of
time.
you. Yeah.
Thank you so much, sir.
It was nice to talk to you. So all the best and take care. Good night.
Thank you, sir. Yes, sir.
You, sir.
Okay, thank you, sir. Thank you very much, sir.
So all the participants, please be stay connected. Our next session is going to start in this couple of minutes. I already shared the feedback from of this last session, so kindly fill it. Do not leave the group. Bansal sir, are you there, sir?
Yes. Namaskar.
Namaskar, sir. How are you, sir?
Yes, yes. Good, good. Namaskar.
Okay.
Hello, sir. I'm Yogendra Arya. How are you, sir?
Namaskar. Namaskar, Yogendra Arya ji. Namaskar, namaskar.
नमस्कार सर, कैसे हैं सर आप?
बहुत बढ़िया, बहुत बढ़िया.
ओके सर, ऑनलाइन सर मुलाकात होगी सर इस बार में.
Online is much better than not meeting.
Okay, sir. Yes, Abhinav sir, सुना?
Sir, just a minute. But sir, with your permission, shall we start?
Yes, yes.
Okay, thank you so much, sir. So welcome all the participants to this session 10 of this AICT Atal FDP program. So today we have with us our speaker from very far away, Professor R.C. Bansal sir from Sharjah. So I would like to say something about this, sir. Professor Ramesh Bansal sir has more than 25 years of diversified experience of scholarship, of teaching, learning, accreditation, research, industrial and academic leadership in several countries. Currently, he is a professor in the Department of Electrical Engineering at University of Sharjah and an extraordinary professor at the University of Pretoria. Previously, he was a professor and group head in the ECE department at the University of Pretoria, UP. It's not Uttar Pradesh, it's UP, South Africa. Prior to his appointment at UP, he was employed by the University of Queensland, Australia, University of South Pacific, Fiji, and BRITS Planning, India. Professor Bansal has significant experience of collaborating with industry and government organizations. He has made significant contribution to development and delivery of BS and ME program for utilities. He has extensive experience in the design and delivery of CPD programs for professional engineers. He has carried out research and consultancy and attached significant funding from industry and government organizations. Professor Bansal has published over 500 journal articles, presented papers at conferences, books, and chapters in the books. He has a Google citation of over 24,000 and the H-index of 74. He has supervised 25 PhD theses, 5 postdoctorate, and 5 and currently supervising several masters and PhD students. His diversified research interests are in the area of renewable energy, wind, solar, DG, micro, grid, and smart grid. Professor Bansal is an editor of several highly regarded journals, including IEEE Systems, IEEE System Journals, Electrical Engineering, IDSS, SG. He is a fellow and chartered engineer, IIT UK, fellow Institution of Engineers India, and fellow SAIEE and senior member of IEEE USA. So welcome, sir. Welcome to this Atal FDP program. So over to you, sir.
Okay, thank you, Dr. Avinash, for kind introduction. And I'm grateful for your kind invitation, Dr. Abhinav and Dr. Yogendra Arya. And it is a matter of great pleasure that Department of Electrical Engineering, JC Bose University of Science and Technology is organizing 5 days faculty development program on very important theme. So I'm happy to see that there are large number of participants who are joining. So all the best to them. Without taking much time, let me share my slides. Let me share my slides. Please confirm if the slides are visible.
Yes, sir. Yes, sir. Visible, sir.
And my voice audible?
Yeah, it's audible, sir.
Okay, let me just close my video. One second. So time allowed is, I think, around 1 hour 30 minutes total.
Yes,
time, right?
yes, sir. Yes, sir.
So I'll just try to hopefully present in 75 minutes and keep some time for questions answered.
Okay, sir. Sure, sir.
All right, thanks. I'll just start. So here we are talking about the renewable energy and integration in as we are approaching to this smart grid. So in this presentation, I will be briefly talking about these current trends for electric generation. That we know that electricity we want to generate through renewable energy distributed generation. And then I speak about some of the grid interconnection requirements. I talk about the main renewable distributed generation technology, wind photovoltaic system. Briefly talk about this microgrid, smart grid, to conclude my presentation. As we know that there is major issue with the electric generation through fossil fuels, mainly coal-based generation, which causes the huge emissions. And as you can see that the bigger countries like China, US, India, Russia, Japan, etc., they have significant power of electric generation through fossil fuels. And at the same time, huge amount of emission is produced. So electricity sector is like among the largest producer of emission, equally like it used to be this transport sector. And for that also we are seeing the alternative means through electric vehicle sector. So this emission in recent time has been the biggest concern. And another major issue we see is that like how many more years we can keep on generating electricity through fossil fuels, because the resources are limited one. Maybe in the next 50 years or 100 years, this fuel may be adjusted. Then what's the alternative with? So worldwide we are looking for this sustainable and clean means of the electricity generation. So before I start speaking about the renewable power integration, let's briefly talk about this, fossil fuel based, coal based power generation. This is a small scale model for the thermal power generating plant. Boiler capacity is around 30 megawatt and producing electricity of 12 megawatt. Efficiency around 40%. Just very simple model, just to make an estimate that how much coal we are using in a power plant. And through this very simple model, you can make a estimate that how much coal we are using. Then of course, how much would be water requirement, how much would be air requirement for this fuel consumption. Even when we know the air requirement, you can design different pumps, fans size, etc. So without going too much of detail, this small size power plant has the coal consumption, you can see 1 kg per second. And then of course for consumption of this much quantity of coal, it requires 10 kg of air per second. So if you want to estimate like any size of power plant, for example, 1200 megawatt of coal-based power generation. So if you just consider linear size, so it will require 40 kg per second coal for 1200 megawatt. Considering that this simple linear analysis, we can make an estimate that how much coal will be needed. This is, we are talking per second. Then we want to make an estimate for 1 hour 24 hours, 1 year, so we can easily make an estimate. For our country, like we have, coal-based generation around 200 gigawatts. So we can easily make an estimate that how much coal consumption would be there, and we can also get an idea that burning of this coal, how much emission it would produce. It's huge. So, and it is badly affecting the health of the human being, vegetations. So this is a biggest concern recent time that worldwide we are facing. So we cannot afford to have, this coal-based generations keep on going, increasing these coal-based generations. So we are just trying to see the alternative means, how much more renewables we can add, how much we can minimize the generation from the coal-based. We cannot completely shut down immediately because we need the electricity for development. So again, this is a slow phase, and slowly we are, increasing the renewable power capacity. Simultaneously, we are reducing the coal-based generation because meeting the power requirements is very important. So if we see the fuel share in the power sector, which type of fuel mix we are using. So here we can see we are around 2025. So you can see that this is worldwide the fuel share. So you can see that we are using coal share something around 35%, and use of large hydro and nuclear. So this again we can see something around 27%. Its share is slightly declining now because major large hydro sites worldwide have already been harnessed. Use of gas is quite stabilized. So you can see the share around 22%. But our main interest for these renewables, you'll see the current share maybe around 17%. Of course, in this we have not included the large hydro. If you include this large hydro, obviously this share will be more. But the trend you can clearly see that it is increasing. So again, we need several more years when its capacity increases, like we will have by 2040, that this will be the prime means of electricity generation through renewable-based generation. So these current trends for the renewable power generation is through renewable distributed generation, smaller scale unit. Interestingly, with the smaller scale distributed generation, even power generation is economical as well. Normally, past approach was that we have larger generating units, then it will be economical, because with the small scale renewable based distributed generation, these are economical as well. The reason for that being is that these renewable distributed generations are integrated in the distributed system, and they are very close to the loads. Distance between the generation and load is minimal, just few kilometers it can be. So the grid losses, transmission and distribution losses, which are proportional to the distance, they are significantly reduced. And another great benefits we have, that being the green technology, they offer positive impact on the environment. There are several other benefits. One of the review paper written by my researcher. So you can see that this paper very interesting detail, very talks in very detail about this renewable distributed generation, addresses all these issues very well. So we can see that what are some challenges associated with the renewable distributed generation. So some of the challenges are, as we know, that these renewables like wind, photovoltaics, etc., they are highly fluctuating and intermittent in nature. For example, wind speed can fluctuate plus minus 25% in few minutes. Another renewables like photovoltaic systems, during night, no sunshine, during the day, because of the weather conditions, during the day, its insolation keeps on changing. Moving clouds will affect the power generation. So these renewables are fluctuating and intermittent in nature. Even these traditional networks, which might be 50 years or 100 years old, they have not been designed keeping in view of this renewable distributed generation integration, because at that time there was no concept of like renewable distributed generation. So we need to develop the infrastructure for a renewable energy integration. Another issue that when we integrate the distributed generation, power flow becomes bidirectional. When power flow becomes bidirectional, existing simple protections, which are mainly based on single direction relay, may not work well. So we may need to significantly modify the existing protection scheme. I have supervised several researchers. Many of them have worked on this renewable distributed generation. You can addressing some of the issues like how we minimize this energy loss, integration of distributed generation, finding the location and sizing of the distributed generation. So several research works have been carried out in these important areas. So the paper I mentioned, it tried to explain several benefits we can have from the distributed generations, like the technical, economical, environmental benefits. I will not go into the detail, but they are very, very, very nicely listed here. Even with the renewable distributed generation integration, it can lead to have reliability improvement, voltage profile improvement, of course, power loss reduction, security enhancement, operational advantages, economical benefits, environmental benefits, or we can have several benefits with this renewable distributed generation integration. But we will get these benefits when these renewable energy integrations, there is proper study for optimum location and sizing of the renewable distributed generation. We need to carry out the simulation study before this renewable energy integration takes place. So a proper simulation study, what is the optimum location, sizing, a detailed study is required before actual installation. Otherwise, we may not get these required benefits. Briefly talking about the types and technologies of these distributed generation technologies, we have renewable distributed generations, non-renewable distributed generation as well. Renewables include like wind, photovoltaics, small itself will include like the mini, micro, and nowadays people talk about this pico hydro as well, biomass, biogas, fuel cells, geothermal, many more. Non-renewables like gas turbine, micro turbine, reciprocating engine, etc. Then we just try to have some kind of comparison between the different distributed generation technology. This I'm talking again from the review paper. So here, when we are comparing the different type of distributed generation technologies, so some of these parameters on which we talk about this comparison, what are the nominal range in which these distributed generation technologies are available, what are their efficiencies, what fuel is used, how much is the CO2 emission. So some of these factors. So we are talking about these non-renewable disease, renewable disease. So I'm not going into the detail of this, and I'm happy to provide these slides as well. So here you will see that when we are talking about these renewables like wind, PV, you can see that first important point that the fuel what we are using here, these are free from the nature. Sunshine, wind velocity, they are free from the nature. It doesn't need any cost as we have other types of like these distributed generators like gas or diesel generator, which have a significant running cost. But here, in case of wind, PV, even with this small hydro, basically they are free from the nature. Another great benefit we see from this renewable distributed generation that there are almost no direct emissions. You can see how much emission is occurring from the other types of non-renewable distributed generation. Of course, you will see that one of the concerns what we see, particularly from the photovoltaic systems, its efficiency is low. Typically, we talk about the efficiency something around 15, 17, maximum 20% nominal value. So efficiency is low as compared to others. This is a concern. Engineers, scientists are working to improve the efficiency. Some other types of better materials are being developed where efficiency can be improved. So let's hope that in future efficiency we can improve the efficiency practically, because one of the thing is that when we are talking about the efficiency in the laboratory, efficiency will be high. But as we place the photovoltaic systems in the actual field condition, efficiency significantly drops because of the several reasons, including the operating temperature of the PV panel. So the efficiency is low, but it is not as big concern as we would have like other type of power plant, because in that there is direct cost associated with the fuel. Here at least fuel is free for photovoltaic systems, so low efficiency is not as big concern as we would have in other power plant, other generators like the diesel generator or gas turbine, because here it is fuel is free. Now let us talk briefly about the distributed generation interconnection requirements. There is one IEEE standard, IEEE 1547. So this standard is applicable for the small size distributed generation integration up to 10 megawatt capacity. If this distributed generation is of, or our renewable power plants is of the bigger capacity, then we need to have other standards. So here, this itself standard is a long document, and it can take 2 hours to fully discuss the document. So I have just briefly listed down some of the important requirements in terms of fault rate through capability, voltage and frequency, operating limits, active power control. It further includes like set point, ramp rate, zero frequency regulations, reactive power control, voltage control, other requirements in terms of power quality, protection, etc. Dear participants, please, if you have any queries in between, please keep note down. So I'm happy to discuss at the end as well. So here I will briefly discuss about few things. Like you see, voltage and frequency operating limits. Here these 2 graphs shows the frequency and voltage operational windows for this distributed power generation, wind power generation. Upper one is the case for Denmark, below one is the case for China. So in upper one, you can see that nominal frequency range is between 41 to 51 Hertz. If frequency deviates from this nominal operation, then within the specified period of time, which can be between 30 seconds to 30 minutes, within that specified time, we have to bring the frequency back to the normal operation. So here it is showing the importance of our control systems. So we have to bring the operation back to the normal operation. At the same time, if you see the nominal operation range for frequency, like for China, so you can see frequency range is 59.5 to 50.2 Hertz. So generally, we will think that with the renewable distributed generation integration, quality of power will be affected, but it is not the case. In fact, how these grid codes are designed and implemented. When these grid codes are strictly designed and implemented, so the independent power producers who are not qualitative one, they will not be able to get successful in getting the bids tendering process, so they will not be successful. Then, of course, we have the voltage requirement. That voltage should stay within plus minus 10%. Regulation maximum should be plus minus 10%. Fault rate through capability. That when fault occurs on these renewable power plants, how these renewable power plants will behave. Past approach was that when the fault occurs, these renewable power plants will be shut down. But now the technology has improved significantly. They are not immediately stopped down, but they stay connected. Not only stay connected, but they help in recovering of the fault conditions. So they can help. I just give you an example. For example, previously we used to have these photovoltaic systems the converters will operate at unity power factors. But now converters can operate on leading and lagging power factor. It means they can contribute reactive power. They provide reactive power support, and by providing reactive power support, they can improve the voltage. When there is fault, the voltage will go down. So they can help in recovering the fault condition. Now let us talk about briefly about these main renewable distributed generation technologies. We talk about these wind power systems, both onshore and offshore. Onshore, by end of 2024, worldwide, its cumulative installed capacity has already crossed 1,000 gigawatt. The countries which are leader in the power generation from this onshore wind, obviously you can see a significant share is from China. Then, of course, US around 15%, Germany and our country doing great as well. So, and of course, many other countries. So this is now quite mature technology. Another type of renewables that we see that offshore, it is now getting very popular. It started mainly is the power generation from the offshore was only some countries in the Europe, but in recent few years, China also started generating power from the renewables. So you can see China's share has something significantly got high. At present, the cost of power generation from offshore is high, but as the technology matures, obviously this cost will come down. As we will see that we have seas for sea coastal areas for many countries, even including our countries. Almost many countries have this sea close to there. So, and you'll see that major cities worldwide are, on the coastal areas of sea. Like, for example, Australia, all these cities you will see Melbourne, Sydney, Brisbane, they are just on the coastal areas. So basically, load is very close to sea where this offshore will be. Offshore is wind turbine if they are installed. So load and generations very close, and so thereby development cost will be reduced. So as technology matures, in this cost will come down, and then we expect that we will have a lot of capacity addition from this offshore wind. Now we see that what is the growth rate every year for this wind. You'll see that basically, for example, at the end of 2024, it was say they spent 1,050 gigawatt. How much we will expect by end of 2025? So this capacity increase would be around 10%. 10% of this 1,050, around like say 100 gigawatt. So end of 2025, we can expect that it goes like say 1160 gigawatt, something like that. So the growth rate in the capacity addition for the wind, it is around 10%. We will see how much we have for the photovoltaic systems as well. Now, the wind installations, wind farms, what we are talking, worldwide, we have several wind farms which are quite big in capacity. Talking particularly about our country, we have two big size wind farms. One in the Rajasthan state, having the capacity 1.6 gigawatt. Another one, 1.6, sorry, typo, 1.5 megawatt. It is in the Tamil Nadu, and worldwide there are several other large size wind farms as well. Now, as I already explained, the cumulative capacity, we are now from wind 2025 already around more than 1,000 gigawatt capacity. How much we can expect, for example, by 2050? So different models have been proposed how much capacity we can expect. So how much we can expect, say, by 2050, we may expect something like, say, 4,000, 5,000, 6,000 in this range. So current capacity already more than 1,000 gigawatt. So the growth rate every year is around 10%. Now let us see the increase in the wind turbine system rating, generator size, and associated power electronics. So you would have seen the researchers who are working in this wind technology. You might have seen this figure, very popular, coming from this paper. So the wind turbine technology for power generation, it started mainly around 1980s. At that time, wind turbine rating, average wind turbine rating used to be around 50 kilowatt. Corresponding wind turbine rotor diameter around 15 meter. The generator technology, what we use is simply squirrel cage induction generator. As we kept moving forward, so the capacity kept on increasing, and of course, rotor diameter as well. When we moved from squirrel cage generator to wound rotor induction generator, as you know, in wound rotor induction generator, like in year 1995. So this capacity gone to 1,000 kilowatt, 1 megawatt, rotor diameter 50 meter. The generator technology, wound rotor induction generator, through which we can add the resistance in the rotor circuit. Then around 2000, we had the very popular generator technology, W-fed induction generator. So this generator is still very popular for power generation. The rotor diameter capacity gone to 80 meter. In W-fed induction generator, we have the power electronics rating 30%, converter rating is 30%. The size of the wind turbine kept on increasing, and the diameter as well. So we had another very popular generator technology, what we call as the permanent magnet synchronous generator. So in permanent magnet synchronous generator, we have this the converter rating, which is same rating as that of this generator rating. So this the power electronic ratings will of course add the additional cost for the system, but it will make the wind power system operation variable speed operation. We can have extract more energy, so these costs can be compensated. There are several other, generator technology. Is some of the papers published in this components journal, a special issue. I think around year 2015. So researcher interested, they can refer details about this generator technology. Now, very recent trend, you can see the size of these offshore and onshore wind turbines. What currently we have, like in year 2023, in offshore, we had a single wind turbine size 18 megawatt, and it has blade diameter 280 meters. Whereas for this offshore, we have the single wind turbine of the power rating 10 megawatt and this blade diameter 220. By 2030, we expect that this capacity would go up to 25 megawatt with the blade diameter 350 meter for the offshore, and for the onshore, we expect that this capacity can go 15 megawatt from 10 megawatt, and the rotor diameter can go 270 meters. So just try to think that how big are these wind turbine blades. We have football ground, which is around 100 meters. So these wind turbine blades, what we are talking, are 3 times bigger than this football ground. Can you imagine that how big are these wind turbine blades, how they will be erected, commissioned, maintained? So it is a challenging task, particularly inside the sea. See how we install, how we operate, how we maintain. So it is highly challenging task. Then very important point I want to mention that why we are going for the larger and larger size of wind turbine size. As we see that there are so many challenges, obviously, but as you will see that very popular equations, power available in the wind, everyone will know, half rho A VQ, where rho is the density, V is the wind velocity. Obviously, we would like to place the wind turbine where there is good wind velocity. Power will be proportional to the cube of the wind velocity. Area is pi by 4 d square. So the relation between the diameter of this wind turbine blades and power. So power is proportional to square of the diameter. I give a simple example. If we have diameter, say 10 meter, power produced will be 10 square, 100 units of power. But if the diameter goes from say 10 to 20, power produced will go 20 square, 400. So power produced changes from 100 to 400 when we are increasing diameter from 10 to 20. When we are just doubling the size of the diameter, power produced goes 4 times. So there is economy associated that when we are increasing the diameter, power increases significantly. Of course, cost will also increase. The cost increase as we increase the diameter, say from make the diameter double. So cost increase will be in same proportion. As we double the diameter size, cost will just become double. But power produced will go increase by 4 times. So there is economy associated with the larger size of wind turbine. That's why we go for the larger and larger size of wind turbine. This you can see a very small size wind turbine. In fact, several years earlier, I examined one PhD thesis from the Victoria University, Australia. So researcher conducted the possibility for this small size wind turbine installed on the rooftops of the building. Obviously, you can see that this is a vertical axis wind turbine. So this vertical axis wind turbine will cause less stress on the rooftops of the building. So if in future this kind of small size wind turbine, if this technology matures, in future we may say that where there is good wind velocity, the small size wind turbines are also installed on the rooftops of the building, maybe along with photovoltaic systems. Now let us talk about the another technology, photovoltaic systems. So how much power our Earth surface will receive from the sun in terms of sunshine, and that we convert into the power. So on an average, Earth surface will receive power of the order of 1.2 into 10 raised to power 8 gigawatt. And if you can take this power just for 1 hour from the sun, so this power would be sufficient to satisfy the demand for whole year for the whole world. So we just tap the power from the sun for 1 hour. This power would be sufficient to satisfy the demand for the whole world for 1 year. So you can see that how much potential we have got from the sun. And you see how the other great benefits we have from the photovoltaic systems. How electricity is generated from photovoltaic systems. Simply, we have PV panels. We place the PV panels in the sun at an optimal angle, and it simply produces the electricity. If you talk about any other type of power plant, maybe coal-based power generation, we have coal from the coal mines. Then coal is crushed, burnt in the boiler, produces the steam of required temperature, pressure. It runs the steam turbine. It runs the generator and producing the electricity. So many stages are involved. And then additional benefit we see from this PV generation, that it is very much environment friendly, highly reliable, because it does not have any moving parts, completely silent operation. If we have PV generation from very close, no noise at all, very low operation and maintenance costs. Just it needs regular cleaning of these PV panels to avoid the dust accumulation, and these PV systems can be installed very quickly. Big size of power PV system power plants, maybe they can install within less than a year. It can be operational within less than a year, as compared to other types of power plants. For example, large hydro, coal-based, it can take 5 to 8 years from commissioning the time it becomes operational. So we have got the great advantages from these photovoltaic systems. So now this technology is increasing at very fast pace. So these PV, different types of configurations, the photovoltaic systems can be connected to the grid, or they can operate in the isolated modes as well, where they can be mounted. If you have very small size PV panels, as we see on the street lights, it can be mounted on the poles. It can be mounted on the roof of the building, or in some case, it can be part of the building itself, what we call it the building integrated PV systems. When we have this very large size PV plants, it will be placed on the ground. So this figure shows a very simplified grid connected PV systems generating the DC power. Then we have this power conditioning unit, mainly the converter, which will convert from DC to AC because most of the loads are AC. The power will be fed to the homes. Then there is another supply from the grid. Like for example, in the night, there is no power from the PV, then we draw power from the grid. And during the day, if there is excess power generation from PV, it can fed back into the grid as well. So there is a concept of net metering as well. These PV systems can have its operation in the remote, isolated areas as well. So here we will have PV systems, then there will be a backup systems in terms of battery storage systems. Additionally, there may be a diesel generator as well. Then of course we have like inverters, control panel associated with that as well. The another application for PV systems can be in the irrigation system. So it can be very important, very useful for countries like ours, where we have significant irrigation system. So here in this case, we have simply photovoltaic systems, a DC motor, because PV is generating DC, and then a pump. So here we are not having any like storage system because we want to have this least costly systems for the farmers. So whenever there is sunshine, it will run the DC motor and it will start pumping. So what is the cumulative PV rating? What are the top countries producing the PV photovoltaic power from the photovoltaic systems? So you can see that this PV generation started quite late as compared to wind. Wind it started around 1980s, but you can see generation from PV, something started appearing around 2010. And then you can see in the last few years how the capacity, worldwide capacity is growing. Because previously, one of the major issue, it used to be that the cost of PV panel, it used to be huge. The cost of power generation from PV was high. Now cost has come down. I'll show in the coming slides how much the current cost. So cost issue is gone, and as you have seen that PV system integration, it is very easy. It can be in very small size, can be medium size, or in the large power plants as well. So it is very user friendly. Lot of advantages. So you can see how this capacity addition is growing exponentially. We see that the capacity addition every year, it is huge. Like you'll see that the capacity addition every year. So this growth rate is something around 25%, 30%. In wind, we had this around 10%. So wind system capacity it will take 10 years to get the capacity doubled. Whereas in photovoltaic system, within period of 3 or 4 years, the capacity will just get doubled. The countries which are leader in the power generation from photovoltaics, these are of course China, European Union, USA, and I'm very happy to mention that our country is really doing great. I'm very delighted that our country is doing exceptionally well. Of course, there is no comparison. We are not comparing. Different countries have their different requirements, but the way our country is doing is something great. And we see that if you see the data like 1 or 2 years old, you'll find a lot of changes. So we are very proud of that. Like you can see this slide showing this like the global PV market evolution of the new annual capacity in the major markets. So showing something compound annual growth rate 2022 to say 2024. So if we see like growth in this showing for this lighter blue 2023, then dark blue for this current one 2024. So if we see for example China, the first year growth rate was like say huge 163% highest. The next year growth rate go down to like just 50%. US is nominal. When talking particularly our country, the growth rate like for this year 23-24 is like 145%, like huge. Comparable is like China. So we are really doing very great in this photovoltaic technology, and we should be very proud of that. We have got like this very big size photovoltaic power plants in our country. 2 power plants, one in Rajasthan of the capacity more than 2000 megawatt. I previously worked in the BITS planning during 99 to 2005, 99 to 2005. At that time, we used to have a collaborative program with our utility, National Thermal Power Corporation. Their business is the electric generation in coal and gas power generation. This NTPC supplies around 25% of our power generation. So I visited almost most of the power plants for the NTPC. So they have mainly business in the coal and gas power generation. So we got one this big size power plant in Rajasthan state. Another one we got in the Karnataka state, around similar size, more than 2000 megawatt. If we have any plant more than 2000 megawatt capacity, we call it like the super thermal power plant. So we are reaching for this PV like super thermal power plant as we have like for this coal based power plants. Then this NTPC, now they are expanding their business from coal and gas to even in the renewables, because currently their energy mix is around 96%, mainly power generation from coal and gas. But they, in this coming 5 years, they want to diversify their portfolio to like 70% from coal and gas. Then 30% from the renewable power generation. Several other countries are also having these large size power plants. So these photovoltaic systems, we can connect to, very small size, like on the street light, small PV panel, to like this commercial university buildings, any government buildings, going to very large size power plants. So we have quite flexibility with this photovoltaic system. I worked briefly at the University of Queensland, Australia, and I worked during the 2008 to 2013. Around year 2012 or 13, we used to have a 5 megawatt photovoltaic systems. This university has got like this 3 or 4 campus. If we add all these campus, so the capacity at that time used to be 5 megawatt. Through this website, you can find a lot of interesting information about these photovoltaic systems, the practical experience, what are the different types of PV panels are being used, what are the battery technologies, a lot of practical information you can get from this website. Even previously through this website, in the real-time system, you can see this graph during the day, how this power generation is taking place since its installation, how much total energy it has generated, how much savings it has made, avoiding these CO2 emissions. So you can find a lot of interesting information. Now, when we have this PV integration, some of the issues we have, it will depend upon what is the size of PV systems, where it is being integrated. If you have small size, obviously integration will be in the distribution system. In the small size power plants, we'll talk about the issues like this moving clouds. If we have, significant capacity addition in the localized area, in some of the city, if there is some government rebate scheme, large number of people have their own photovoltaic systems. So as we know that during midday, power generation from PV is significant, but during the midday, the power demand is minimum. So with the localized significant integration, there can have voltage and frequency variations as well. Now, when we have like the large size power plant, if they are integrated, we're talking about the issues like the how this large size PV plant will impact the overall stability of the power system. Then interestingly, when we have these photovoltaic systems, should there be any storage system or not? Of course, they are connected with the grid as well. If there is storage system, which way it can be useful. So this is an example of photovoltaic integration at the University of Queensland. So it has the storage system as well, battery storage system. So this storage system can help the utilities who supported these PV systems. So it can help the utility in managing their peak demand. When there is peak demand, so the energy stored in the battery can help in maintaining their peak demand. Few years ago, I think around 2021, the University of Queensland had its own 64 megawatt solar power plant. Any university having such a big size of photovoltaic power plant is really great. So this PV plant, it will generate electricity, it will feed power into the Queensland network, and university may have some agreement. They are feeding power at some point in the grid, and whatever power needed, they can get power from some other point in the grid where they need it. So this power can be fed in the Queensland network, and then it can supply power to the homes in the Queensland state. So this is comprising of, like you can see, 2 lakhs PV panels which can generate power 160,000 megawatt hours per annum, and this can be equal to more than 25 homes. So this is a great example. You can see that this facility, of course, generating power in the real power system, but this can also conduct realistic research on the photovoltaic systems as well. Now, little bit talking about few more issues. As we have these renewables coming up significantly, we will have, some people will have some concern. Are these renewables really renewables? Are there waste being produced from the PV panels, etc.? So everything has to be some way a compendium. So here this paper published in Nature Physics in 2023. So it compares the different waste, and it goes from year 2016 to 2050. Still we have like 25 years. So as you see the wastes, like from the municipal waste coming out from these coal power plants, cumulative wastes, plastic waste, and when we compare this with respect of like PV module waste, so comparison, like you see, this waste coming out is very minimal as compared to other types of waste. Then additionally, like we have not gone a complete cycle for the photovoltaic systems, as the power generation mainly started around year 2010. Then they have PV system have useful life around 25 years. Engineers and scientists are continuously working how to reduce waste from PV, how to find some reusable means. So the wastes with these renewables is comparatively very less, and it is not is that much a big concern. Now let us see the situation of power for our country. So we have this total power generation as shows few months back. So we have power installed capacity 500 gigawatt. So this capacity in this we have slightly higher, around 51% from the non-renewables. Coal mainly 45%, oil and gas 4%. We have 1% nuclear. So total power generation 252 gigawatt, around 51% we have from the non-renewables. Talking about the renewables, so we have quite close to that, 237 gigawatt, 48.5% we have from the renewables. When we are talking these renewables, we are of course including the large hydro, which is obviously renewable as well. So we if we see the renewables here, so we are doing very well. And then additionally, like whatever we used to hear, we had been continuously hearing that always we have like the gap between the generation and demand, something like 20%, 15%. So that is a past history. Now we do not have like the shortage for power generation. Of course, we are a growing economy. Our load keeps on changing drastically. I'll give you an example. For example, US, for the past 10 years, there is almost no increase in the load. Even load might have a little bit decrease as well. And for our country, like growing economy, our loads keeps on drastically increasing. So meeting the power demand is not an easy task, because government have several sectors they have to take care. So they have quite challenging role, but we are very happy that there is no shortage of power. But of course, like we need to do lot, even the managing with the existing power plant in a very well manner is very important, because just keep on adding capacity but not maintaining very well the existing power plants, it doesn't serve the purpose very well. So here you can see from this like another slides. This is again from the CA, Central Electricity Authority. So you can see here our small size renewables percentage 38.8%, large hydro 10%. So we are close to just like say almost around 50%. So we are doing very well in the renewables particularly. If we see further breakdown for these renewables share, you can see the share of the solar 64%, wind 27%, then bio and small hydro. Now talking about these renewables, as we are expanding renewables. So what is potential in our country? Renewables like wind, of course, when we are estimating the wind potential, it has to be estimated at a particular height. If you make an estimate like in a height at 100 meters, so we have got potential around 300,000. The current installed capacity around 40,000. So we have got huge potential. We have tapped very less part, around means like 10 or 20%. Then we have got like this huge potential for the solar as well. Of course, the installed capacity like this slide might be old, but we already see that how much installed capacity we have got now. So of course, we can see that the solar large size power plant, it will need the huge space. 50 megawatt PV system will require a space of around 1 square kilometer. So it needs significant space as well. Then bio, we have like this good potential, small hydro, some other renewables. Mainly we are talking about this wind. Major you see that renewables, what we have is a wind, and solar. So we have got very good potential, and we are quite expanding very well in this area. I mentioned also offshore as well. So in future, as the technology matures, cost down, we may start producing power from these offshore wind as well. Now I talking some further issues about this this wind power generation. In fact, I examined some thesis from this Gandhigram in Tamil Nadu. So some of the issues very nicely explained. We are reaching close to the time, so I'll just go a little bit faster. So the issues, as you see, that these renewables need the huge space. Whatever we are talking about this, whether it is wind or photovoltaics, it needs the huge space. In wind, we need to keep the some appropriate spacing between the different wind turbines. It could be something 3 to 5 times of the diameter, or even more than that. So in between, we have significant space, so which can be utilized for keeping PV panels in between. Even these wind power plants, many of these wind power plants, they have gone for their useful life. So these wind turbines can be replaced by bigger size wind turbines retrofitting. So this space utilization can be done very well. So finding the new space is really challenging. Talking about the cost, you can see this is coming from our Ministry of Non-Renewable Energy. Cost of wind and PV, if you talk 10 years earlier, it used to be 6 rupees, around 6 rupees per unit of electricity. Now this cost has come down for wind around 3 rupees, solar slightly lesser than 2 rupees per unit of electricity. Even for the solar, you are seeing still it is going down, so there is scope that it can go slightly lower than that. But for the wind, you see that came to 3 and then trend is going a little bit on upside. So for wind, decreasing the cost may not be visible further because of the cost of the materials, steel, these materials being used, and decreasing cost further may not be feasible. But this PV technology, it has not yet fully matured. The cost can go further down. So you can see that particularly these renewables, they are now the cost is no more issue. They are very well, comparative, and they so this capacity addition, particularly from this PV, is going in the big way. Our government plans have great plans that we want. Our government wants to boost renewables up to 500 gigawatt by 2030. Currently, we are, as you have seen previous slides, we are close to 250. So next 5 years, our target is to add another 250 gigawatt by 2030 in 5 years. So it is like a challenging task, but the current government doing very well, and we expect that we will close to this target. And our target is to reach net zero by 2070. So we are doing very well. We are very proud, and hopefully we achieve this target. The another technology what we are talking is like, say, microgrid. It can be connected to the grid. It can be in the remote areas, particularly when this hybrid power system we are talking in the remote we have this mainly power generation through diesel generators. Power produce is extremely costly because of the cost of fuel, transportation costs, operation and maintenance costs. Long back, I worked few years in Fiji Island, a small island country. Power, small, very small country, population around 10 lakhs. So, power installed capacity, not something huge, very less, 400 megawatt. But the point what I'm trying to mention, their diesel capacity is significant, like 20, 30%, 35%, something like that. So out of 400, more than 100 megawatt or even higher is coming from the diesel generator. So the cost is significantly higher. How this cost can be brought down? By adding the renewables, whichever resources are available in terms of wind, PV, whatever resources are available, just integrate along with diesel. The communities can be supplied power for several hours, because when we talk hybrid, they say the community will be supplied just minimum basic power, 2 bulbs, 1 fan, only for few hours. Why not? They can be supplied power for almost continuously, and they can have some other devices, television sets, trees, so to improve their quality of life. So hybrid power system can be a great technology in this regard. As we are approaching time, I could have explained this slide itself more than half an hour, but we have this time constraint, so I'm just going a little bit faster. So this slides again published this in the paper in 2015, slide bit old, but it compares different renewable energy technology, wind onshore, offshore. We talk photovoltaic systems. We talk some other technologies, like particularly we are talking about this now coming up, like the fuel cell, batteries, hydrogen storage. Batteries very important when we are talking sustainable integrations, even the electric vehicles. It talks about some of the challenges. The trend we already reached to 2025. There are some challenges, but because of time constraint, I'm a little bit going faster. Then talking briefly about the smart grid. So smart grid has 3 subcomponents: infrastructure. When we are talking infrastructure, in terms of like power generation, transmission, distribution, power generations from renewables, microgrids, electric vehicles, vehicle to the grid, grid to the vehicles, smart information systems, smart meters, sensors, phasor measurement units being used in the long transmission line, communication system, wired or wireless. Then how this smart grid will be maintained, what will be the management objectives, minimize the emission, reduce the cost, and so on. Then what tools, techniques will be used, conventional programming, intelligent programming, machine learning, and so on. The maintaining the privacy and security of the data extremely important. How this smart grid will be protected. So this becomes important aspect. Now, what we are seeing that smart grid is not like the complete replacement of the existing grid, but to complement it with the features. We need to have both centralized and distributed generation, integration of more and more renewables. Electric vehicles are coming up. We need to have storage systems, phasor measurement units, smart metering, make use of IT to optimize the capital assets, reduce operation and maintenance costs. So with respect to conventional, in the smart grid, we need to have power generation both from centralized, even with the fossil fuel based as well, adding more and more power from renewables. Electric vehicles are coming, power flow is becoming bidirectional. There is two-way communication. Utilities can communicate to the customers. Customer can communicate to the utilities. Customer can optimize their energy bills. The conventional meters are likely to be replaced by these smart meters. This smart grid expected to have self-monitoring and self-healing properties. At the end, how the customer get benefited from this smart grid, customers expect to have choices. There should not be like a monopoly system, only one utility in the area, but we expect that there are at least two, three utilities operating in the same way, in the same area, so that customer have choice and they can get quality of power supply at competitive prices. So we are just almost at the end of the presentation. And I have quite a large number of students, researchers who have significantly contributed in the research. I would like to acknowledge them in terms of books, book chapters, research papers, and these are my contact details. I will just like to stop discussing, and I would like to happy to take some questions. Thank you all for your kind attention. I'm happy to take some questions. Thank you all.
Thank you so much, sir. It was really a highly wonderful and highly informative session, sir. So is there any questions from the participant side?
Sir, I have a question.
Yes, please, when anyone asking questions, just very briefly introduce from where you are.
Yes,
like
sir.
that.
So myself, Dr. Bipasha Patra, and I am from Jalgaon, Maharashtra, Raisoni Group of Institutions.
Yes, please.
Sir, actually, this is my topic of research in PhD. Means I was working with PV module and inverters with MLI to reduce
Yes,
the
yes.
power harmonics.
Okay.
So I actually want to pursue postdoc in the same field because it has high potential. So I just heard in your introduction that you have guided many postdoc students. So it would be very enlightening if you could just tell me that how should I proceed with the postdoc applications if I want to go to it, because regarding how to write a proposal and how to go for the problem statement, that particular part, if you could just give me some reference, because I am into an urge that I want to go for postdoc in this year itself. So please, if you could enlighten.
Okay, very nice. So you already completed your PhD, or it is?
Yes,
what is
I
it?
have completed my PhD. Now I am going for postdoc.
Okay, this is like in fact very very good questions, not only from one participant, but this is obviously give interest for almost all these researchers. To give you this realistic pictures, like this postdoc, like any university or any professor will have postdoc. So obviously the thing is that from where the funding will come. So either any professor will have some projects having some funding, so in that he or she will advertise for the postdoc positions. Sometimes some university will have their own funding and they will distribute across the university from some researcher, they will advertise that. But obviously you cannot expect that every faculty member can invite anyone as the postdoc, because the main thing is that any professor should have some good amount of funding. So one of the thing is that and you cannot target like say one professor, or of course any researcher can write to potential professors, but the point what I'm trying to mention, that there are few websites, free websites in some countries, so you can just subscribe to those websites, like in for example in Australia there is like SEEKit, SEEKit. So you can freely subscribe if there is any opening. So you'll come to know there is opening and one can apply. So rather than just focusing on like only few, first thing is that if there is in general any advertisement for the postdoc, at least we know that there is some advertisement, and then whichever is relevant, one can apply that. So this is little bit I try to give you an idea, and like if there is something more detail, I will be happy to explain.
Sir, a very related question. Actually, I applied for the NRF postdoc proposals, but most of what we observe in India that postdoc options with scholarship, as you mentioned, are rightly for the IITs and NITs. I also have written individual mails to IITs and NITs to some professors. From few, I have received the reply. But do private universities in India who have good research facilities also allow postdoc through their websites?
Yeah, so like this some good universities are also coming up because they want to now expand their research works, because if they have to be in the good ranking and improve their research, so they have to also come up so at least few universities I know, for example, BITS or several others are also slowly coming up, and there is a possibility that they will also try to start like this postdocs, because obviously postdocs will be paid comparatively lesser than this regular faculty, and they can contribute in terms of research, mainly in the research, but at the same time will be contribute in the teaching as well.
Thank you so much, sir. I would request the organizers to please share the contact information with the permission of expert if possible, so that I can get into personal touch and work it out further.
Please, you can take picture or I can share the slides. So these are my emails. Any participants is more than welcome to contact me. And I will try
Thank you
to-
so much, sir. So much, sir. It was very enlightening. And with the real insights, actually, it has become very clear that how much potential this PV is actually having. We are working for EVs and all, but simultaneously, I guess, with your interpretation of PV modules and solar, it becomes very essential at this point to integrate.
TV, you see that I show you like 1 hour, like there is whole power from the sun, we can take it. So it is sufficient for whole world for 1 year.
Exactly. And whatever the graph you showed for 2024, that shows that it has huge potential if we utilize it properly. Connection issue. But like
Yes, sir.
but I just want to add, like as we are more spiritual people, so as what we have done in the past, like this, I can speak little bit in Hindi as well, so many people can appreciate what we have done. Like this dohan, like as we are, गाय से दूध निकालते हैं. When we are doing a beyond a limit, so what we have done, like this, पृथ्वी का दोहन इतना ज़्यादा किया है, and that is causing bad effects like in terms of environment. So as we have 5 tattvas, including this earth, and then we need to exploit other tattvas like the sun and wind, so which can be, air and sun. So we can extract power which will be like more clean and which will balance, rather than just, making misuse for only one earth. And then if we have, extract something beyond a limit, so it will have, many side effects, bad consequences, like in terms of environment. So we just try to, like say गाय से ऐसा नहीं जितना दूध निकाले फिर उसको इंजेक्शन लगाएं. So this is what we are doing. So earth, we are trying to extract resources beyond the limit. Of course, there is limit. So how we try to balance? We try to find some alternative means So I think that's very important. Please ask
You
some
are-
more
you are
questions.
right, sir.
Yes, yes.
You are right,
Yes,
sir.
yes,
You
please, please.
have delivered an excellent lecture.
Yogendra ji, boliye.
Yes, you are right, sir. You have delivered an excellent lecture. So, I have one question.
Yes, yes.
Hello.
थोड़ा easy पूछिए. अगर difficult हो
in
तो थोड़ा easy
renewable-
पूछ लीजिएगा. हम लोग जॉब नहीं.
Okay, sir. Okay. In renewable sources, the solar portion is
Yes, yes.
increasing year by year.
Yes,
So we know that this is the inertia-less source. So, sir,
Yes, yes.
how will it affect the grid stability? It is my question, sir.
Yeah, so yeah, that's very good question. In some of the research, we come across these things that when we are replacing this rotating generator by means of the static generator, there can be some stability issue, and sometimes we see that how much renewable shares we can sustain. Some research will see that maybe we can reach 100% renewables. So basically, again, we are replacing this rotating generator with the static generator. There is concern, but like again, as you see, we can go some good capacity from the renewables. Even you see that renewable share currently is not very high. Total renewable share I showed you worldwide around 15%. PV maybe 10%, whatever is there. So still we have huge scope to go 30%, 40%. Again, on the top of that, how much we can go from the renewables. Basically, you'll see that how robust is our network. At the end, when we model the electrical power systems, how much is the impedance, short circuit ratio, power system will work according to that. If our power system is really very robust, so there is no issue about the stability. So it will depend upon how robust is our power system network, how we can make our power system very robust. But like as I mentioned, currently is PV share is not very significant, so still we have very good scope. We should not worry or have fear. But again, I mentioned that we should have very robust power system to keep on adding capacity.
Okay, thank you very much, sir.
Thank you so much, sir.
Any more questions?
Yeah, I have one question. I have one question,
please.
sir.
Abhinavji, please ask it.
Actually, yeah, sure, sir. Thank you, sir. So if we talk about this, especially renewable energy, especially the solar photovoltaic, as
Yes,
we know that the life of a normal solar photovoltaic is around 10 to 15 years. Because year by year, the panels are degrading. So what we can do in the solar panel so that the maintenance and reliability can be assured, sir? Normally, it is required to be.
Yes, it's a very good question. In fact, I think life of PV panel could be around 20-25 years. But of course, like other components, converters, batteries, their life 5 years or something like that. Converters different, 10 years or like that. So these components, of course, have to change. But PV panel, I think, can go up to 20-25 years. So I think normally PV systems mainly it needs regular cleaning for the dust to get the required power. Depends on different areas how much cleaning should be done at what interval. Here in this in this UAE or this area, lot of dust, so it needs very significant regular cleaning. But other than that, I think this generally managing PV doesn't need much care.
Yeah, thank you, sir. So, is there any more question from the participant side? Any questions? I think no questions from the participant side, sir. So it's just
Okay,
a
so I would like to, first of all, I would like to thank yourself, Dr. Abhinav and Dr. Yogendra area, so organizing this FDP in a great way.
Thank
As
you,
I
sir.
can see, there are a large number of participants. How many registered or attending? It's good, very good number.
Around 120 have registered, sir.
150, so it's a big number. So this shows that researchers great interest in this faculty program. So this is in fact great way to get the knowledge in the short integrated time. And I would like to thank you all, organizing team and the participants, all the best. As I shared my contact details, anyone having any queries, so are more than welcome to contact me. I would like to thank you all the best. Thank you all.
Sir, 1 second, sir. Actually, there is a formal closing ceremony of each session. So it is just on behalf of Department of Electrical Engineering, JC Bose University, YMC Faridabad, I, Dr. Abhinav Saxena, in the assistance with Dr. Yogendra Arya, would like to extend our sincere gratitude and thanks for your insightful and engaging section. Your expertise, real-world examples greatly enrich the learning experience of all the participants. So thank you once again, sir, for your contribution to the successful of our FDP.
Okay, thank you
sir.
all the best. Thank you.
Thanks. Can we have a group photograph, sir?
Yes, please.
Okay, fine. Kashika? So I
Yes,
request
sir.
all the participants, please switch on your camera for the group photographs.
Done, sir.
Okay, thank you. Thank you so much, sir.
Thank you, Namaskar.
Thank you, sir. Thank you for giving your valuable time, sir.
Thank you, sir.
Thank you.
Thanks a lot, sir.
So the participants feedback link, I think there was some issue with the feedback link. Now it has been enabled. Now you can submit your feedback for this current session right now. So with this, we are closing this session 10 of this day 5. And tomorrow, of course, it is the last day of the FDP. So there will be 3 sessions, and the first session will be started from 2. So let me tell you in brief, there will be 3 sessions. First session will be from 2 to 3:30. Second will be from 3:30 to 5, and the third one is from 5 to 6:30. And from 6:30 to 7, we will have a valedictory ceremony of this FDP. And from 7 to 8, you will have to attempt for a quiz. So it will be last day of this FDP. So it is my sincere request to everyone, please give your 100% and be present in this FDP. Okay. Thank you so much. Thank you so much, everyone. Thank you for giving your time.
Abhinav sir, sorry to interrupt you. I just had a question. Are you going to share the peer recordings or the PPTs of the experts?
Yeah, I'll give it to you, ma'am. Once this FDP is over, I'll upload all this. I will upload all this recording of all these speakers on the YouTube as well. So I'll share you the links of all the sessions, ma'am.
Thank you so much, sir.
Kashika?
Yes, sir.
Now we can stop the recording. Okay.
Okay, sir.
Okay. Thank you, everyone. Once again.